Look up at the night sky from the Southern Hemisphere, and you'll see it, a faint, wispy cloud of light that seems almost detached from the starry canvas around it. That's the Small Magellanic Cloud, a companion galaxy to our own Milky Way, drifting through the cosmic dark at a distance of 200,000 light-years. For centuries, it was little more than a smudge in the heavens, a celestial curiosity noted by early navigators and astronomers. But today, we know it holds secrets far stranger and more spectacular than anyone could have imagined. Hidden within its star-studded expanse are objects that defy explanation: cosmic anomalies, stellar mysteries, and structures so bizarre they challenge our very understanding of physics itself. This isn't just another corner of the universe, it's a treasure trove of the unexplained, waiting for us to explore. Imagine a place where stars are born in violence and die in silence, where nebulae glow with the light of elements forged in stellar hearts, and where entire clusters of stars move in patterns that seem almost intentional. The Small Magellanic Cloud is one of those rare places where the universe feels both ancient and alive, a dynamic laboratory where the rules of nature are written, broken, and rewritten. It's a dwarf galaxy, yes, smaller and less structured than our own, but what it lacks in size, it makes up for in sheer wonder. Here, astronomers have found objects that shouldn't exist, energies that can't be explained, and formations that hint at processes we're only beginning to grasp. Every new observation peels back another layer of mystery, revealing just how much we still have to learn about the cosmos we call home. In this video, we're embarking on a journey to uncover 30 of the most astonishing objects ever detected within the Small Magellanic Cloud. From runaway stars tearing through space at unimaginable speeds to ghostly remnants of supernova that echo with the violence of their birth, each of these discoveries tells a story of chaos, beauty, and the relentless curiosity that drives us to look deeper into the dark. We'll explore glowing clouds of gas where new worlds may one day form, encounter black holes that lurk unseen, and witness stellar collisions that rewrite what we thought was possible. This is more than a list, it's an invitation to witness the universe at its most creative, its most extreme, and its most mysterious. So join me as we venture into one of the most fascinating regions of space ever observed, a place where every discovery is a reminder that the universe is far stranger and far more wonderful than we ever dreamed. Our journey begins not with a star, but with the ghost of one. Drifting within the faint glow of the Small Magellanic Cloud is a cosmic echo of a violent death, a remnant known to astronomers as 1E0102.27219. This is the scattered debris from a star that ended its life in a cataclysmic supernova explosion roughly 2,000 years ago, a time when the Roman Empire was at its peak. What makes this particular cloud of expanding gas so extraordinary is what it's made of and the stunning shape it has taken. While most supernova remnants are a chaotic mix of many different elements, this one is remarkably rich in oxygen, a fact that immediately sets it apart. It's as if the very heart of the exploded star, where these heavy elements were forged, has been flung out into space for us to study. The most arresting feature, visible in X-ray images from the Chandra Observatory, is its perfect ring-like structure. It doesn't look like a tangled web of filaments or a messy cloud. It appears as a delicate, almost ethereal smoke ring floating in the void. This beautiful symmetry presents a fascinating puzzle. A supernova is one of the most violent and asymmetric events in the universe, so how did it leave behind something so perfectly circular? Scientists believe the answer lies in the intricate details of the explosion itself and the way the ejected material slams into the surrounding interstellar space, creating a shock wave that has organized itself into this incredible form. This oxygen-rich ring challenges several assumptions about how massive stars die. Its very existence suggests the progenitor star had a unique history and composition before it exploded, perhaps losing its outer layers in an unusual way long before its final demise. By studying the distribution and velocity of this oxygen, researchers can essentially perform a cosmic autopsy, working backwards to understand the final moments of the star and the mechanics of the explosion that ripped it apart. It serves as a permanent celestial record, a moment of ultimate destruction frozen in time and space, offering us a rare and pristine laboratory to test our theories about the lives and deaths of the giant stars that seed the universe with the elements necessary for life. Not far from the ghostly ring of that ancient supernova, we find a cosmic object that is its absolute opposite, not a site of death, but a stellar nursery bursting with violent, chaotic life. This is N83B, though many astronomers affectionately call it the Space Blob. In images from the Hubble Space Telescope, it doesn't look like the elegant, wispy nebulae you might be used to. It appears as a brilliant, messy, and incredibly bright knot of glowing gas, like a luminous paint splatter against the dark canvas of space. What we're seeing is a region of space where the very process of star formation is happening at a ferocious pace, and it's so intense that it's literally tearing the nebula itself apart from the inside out. The incredible light show coming from N83B is powered by a group of truly colossal newborn stars, each one many times more massive and infinitely brighter than our own Sun. These stellar infants are not gentle giants, they are raging furnaces that flood their surroundings with torrents of ultraviolet radiation. This immense energy makes the vast clouds of hydrogen gas around them fluoresce, much like a neon sign, creating the brilliant blob of light we can see from millions of light years away. But the radiation does more than just light things up. It also acts like a cosmic sculptor, pushing and compressing the surrounding gas into bizarre, bubble-like structures and intricate filaments that give this nebula its uniquely lumpy and irregular appearance. What makes this particular stellar nursery so special, even among the many others in the Small Magellanic Cloud, is its primitive environment. The galaxy itself is considered chemically primitive, meaning it lacks the heavy elements that are common in larger galaxies like our Milky Way. This harkens back to an earlier time in the universe's history, and it changes the rules of physics just enough to affect how stars are born. Without an abundance of metals to help cool the gas clouds, star formation in a place like N83B is a far more violent and extreme process. The stars that manage to form here tend to be overwhelmingly massive, hot, and short-lived, making this blob a perfect natural laboratory for studying the birth of the kinds of stars that dominated the early cosmos. By studying the dynamics within this glowing blob, astronomers are essentially watching the universe's past unfold in real time. They can observe how these massive stars clear out their neighborhoods with powerful stellar winds, how they trigger the formation of new stars in the compressed shells of gas at their bubbles' edges, and how they ultimately seed their environment with the heavier elements that will one day form planets and perhaps even life. N83B is a snapshot of creation itself, chaotic, beautiful, and fundamentally violent, reminding us that even in the vast quiet of space, the birth of a star is anything but a peaceful event. But the serene glow of stellar nurseries and the silent rings of long-dead stars are only part of the story unfolding in this small galaxy. Hidden within its boundaries is an object of immense power and profound mystery, one that broadcasts not in visible light but in high-energy X-rays. This is SMC-X1, a pulsar that stands out even among the most extreme objects in our local group of galaxies. At its heart lies a neutron star, a city-sized remnant of a supernova so dense that a single teaspoon of its material would weigh billions of tons. This incredible object isn't drifting alone. It's locked in a violent gravitational dance with a massive companion star, and this partnership is the source of its terrifying power. The dynamics of this binary system are both spectacular and brutal. The neutron star's immense gravity acts like a cosmic vampire, relentlessly pulling streams of superheated gas away from its larger companion. This stolen material doesn't just fall gently onto the surface. It's accelerated to nearly the speed of light, forming a searingly hot disk of plasma around the neutron star before finally crashing onto its surface at the magnetic poles. The energy released in this impact is staggering, heating the area to millions of degrees and producing the intense, focused beams of X-rays that we can detect across the vast intergalactic gulf. It's a continuous celestial explosion, a testament to the raw, destructive forces at play in the universe. What truly sets SMC X1 apart from every other known system of its kind are its rhythms, or more accurately, its lack of them. A pulsar is essentially a cosmic lighthouse, and as it spins, its beam sweeps past us, creating a regular, predictable pulse that astronomers can time with exquisite precision. This one spins at a furious rate, completing a full rotation in just 0.71 seconds, a blink and you'll miss it flash that repeats with metronomic regularity. Yet, beneath this rapid spin lies a deeper, more confounding mystery. The overall X-ray output of the system doesn't follow a steady pattern. Instead, it undergoes huge, erratic fluctuations in brightness that can change dramatically over timescales ranging from days to years, and our current models of accretion physics simply cannot account for this level of unpredictability. Scientists are grappling with several compelling theories to explain this bizarre behavior. Perhaps the companion star itself has a highly unstable solar wind, causing wild variations in the amount of material flowing toward the neutron star. Maybe the accretion disk where the stolen material gathers is inherently unstable, prone to building up and then dumping vast quantities of gas onto the pulsar surface in irregular, epic bursts. Or the answer could lie in something even more exotic, like the extreme magnetic field of the neutron star undergoing sudden and dramatic reconfigurations, which would drastically alter how and where the incoming material is channeled and ultimately ignited. Each of these possibilities points to a gap in our understanding of how matter behaves under the most extreme conditions imaginable. SMC X1 serves as a powerful reminder that even the most well-studied phenomena in the cosmos can still hold deep secrets. Its unpredictable nature challenges the very models we use to describe the physics of some of the most energetic events in the universe. By continuing to monitor its strange heartbeat, astronomers are not just studying one peculiar object, they are stress-testing the boundaries of our knowledge, probing the limits of physics itself in an environment that we can observe but cannot yet fully explain. It is a cosmic puzzle box, and with every erratic pulse, it challenges us to think harder and look deeper. Leaving behind the intense X-ray glare of that unpredictable pulsar, we now turn our gaze to an object of breathtaking intricacy and beauty, a cosmic jewel that proves even in death, a star can create something truly magnificent. This is the Red Spider Nebula, a planetary nebula whose name only begins to hint at its otherworldly complexity. Unlike the spherical, bubble-like shapes of many planetary nebulae, this one is a sprawling, chaotic web of glowing gas, with two long, opposing jets stretching out into space like the legs of an enormous celestial spider. These structures, known as bipolar jets, are some of the most complex and finely detailed ever observed, telling a story of a stellar death that was anything but quiet or symmetrical. At the heart of this beautiful chaos spins the engine of the entire nebula, the central white dwarf star. This is the exposed, intensely hot core of the star that once was, now stripped of its outer layers. But this is no ordinary stellar remnant. Measurements suggest it is one of the hottest white dwarf stars known, with a surface temperature soaring well over 300,000 degrees Fahrenheit. More astonishingly, it appears to be rotating at a breakneck speed, a fact that many astronomers believe is the key to the nebula's unique shape. This furious rotation, combined with a powerful magnetic field, likely acts like a cosmic garden sprinkler, flinging the dying star's outer layers into space not in a gentle sphere, but in two incredibly focused and high-velocity jets that have sculpted the surrounding gas into this intricate spiderweb pattern over thousands of years. Then there is the matter of its striking color. Most planetary nebulae glow with a characteristic greenish-blue hue caused by the intense emission of ionized oxygen. The red spider, however, lives up to its name with a deep, vivid crimson glow. This dramatic color difference is a direct clue to its unique chemical composition. The dominant red light comes from ionized nitrogen and hydrogen, suggesting that the progenitor star was distinctly different from those that create the more common green nebulae. It's possible that the star's intense winds and ultraviolet radiation were so powerful that they broke apart the more common oxygen molecules, allowing the emission from nitrogen to dominate and paint the nebula in these fiery shades. This magnificent structure serves as a stunning example of how the death of a star is not an end but a transformation. The complex processes at work, the furious rotation, the magnetic fields, and the specific chemistry all combine to create a unique fingerprint in the sky. By studying the detailed structure of its jets and the light emitted from its glowing gas, astronomers can work backwards to understand the life and death of the central star, decoding the physics that governs one of the universe's most beautiful and final acts. The Red Spider Nebula is more than just a cosmic spectacle. It is a dynamic and evolving laboratory, showing us that even in its final moments, a star can create a legacy of breathtaking complexity and wonder. Deep within the heart of the Small Magellanic Cloud, a cosmic construction site of immense proportions is bustling with activity. This is NGC 346, the brightest and most massive star-forming region in its entire host galaxy. To call it a simple cluster of stars would be a profound understatement. It is a sprawling, chaotic stellar metropolis where thousands of young, brilliant stars are being born from vast, turbulent clouds of gas and dust. Its sheer luminosity makes it a beacon visible across intergalactic space, but its true significance lies not in its brightness but in its profound mysteries. This region is a cosmic puzzle, presenting astronomers with a series of interlocking enigmas that challenge our fundamental ideas about how stars are born and how they live their lives. One of the most immediate puzzles is the peculiar and unexpected arrangement of its stellar population. Instead of finding a smooth, even distribution of stars of all ages, observations reveal a strange segregation. The most massive, incredibly hot, and short-lived stars are concentrated in the very center of the main cluster, while a large number of smaller, younger stars are scattered across a vast, extended area around it, connected by faint rivers of gas. This isn't just a single event of star formation. It appears to be a cascading process. The prevailing theory suggests that the furious stellar winds and intense radiation from the first generation of massive stars in the core did not simply blow away the surrounding gas. Instead, this powerful energy actually compressed the outer layers of the nebula, triggering a second and even a third wave of star formation in a concentric pattern around the central hub. It's a stellar domino effect, a beautiful and violent demonstration of how stars can beget more stars. Then there is the matter of the runaway stars. Nestled within this nursery are several massive stars that are moving at absolutely astonishing speeds, velocities so high that they defy the gravitational pull of the entire cluster itself. These are not just fast-moving objects, they are celestial projectiles, tearing through space on trajectories that will inevitably see them ejected entirely from their birthplace. The question of their origin presents two compelling and dramatic possibilities. The first scenario involves a gravitational slingshot. In the dense core of a young cluster, a close encounter between two binary star systems can act like a cosmic Q-shot, with one star being flung away at tremendous speed while the others recoil in the opposite direction. The second, even more violent theory points to a stellar explosion. If one star in a tight binary pair suddenly goes supernova, it can literally blow itself apart. The sudden, asymmetric loss of mass instantly releases the companion star, like a stone from a sling, sending it racing off into space at the same orbital velocity it was previously traveling at, but now with nothing to hold it back. NGC 346 offers a uniquely pristine environment to study these phenomena, because the Small Magellanic Cloud lacks the heavy elements common in larger galaxies. The gas within this nebula is much closer in composition to the raw material of the early universe. This changes how heat is dissipated within the collapsing clouds, which in turn affects the size and type of stars that can form. Here, the process is more direct, more violent, and in many ways more revealing. By mapping the motions of every star within this vast complex, astronomers are piecing together a dynamic history, a story of triggered birth, chaotic interaction, and dramatic escape. It is a living laboratory where we can witness the fundamental forces of creation and destruction playing out on an epic scale, providing a window not only into the current state of a dwarf galaxy, but into the very processes that built the first galaxies billions of years ago. While the sprawling stellar metropolis of NGC 346 shows us the vibrant present of star birth, our next discovery points to a far deeper and more fundamental cosmic mystery. Tucked away within the bounds of the Small Magellanic Cloud are not just individual stars or nebulae, but entire miniature galaxies in their own right. These are the so-called blue dwarfs, and their very existence within a larger dwarf galaxy creates a puzzling Russian nesting doll scenario that defies our standard models of how galaxies form and evolve. The name itself is a clue to their nature. They appear as intensely blue, compact knots of light, a color that betrays the presence of countless young, massive, and exceedingly hot stars. What makes these objects such a profound enigma is the sheer ferocity of star formation happening within them. They are undergoing what astronomers call a starburst, a period of frantic stellar birth that is wildly disproportionate to their size. In a large spiral galaxy like our Milky Way, star formation is a relatively orderly and steady process, but in these blue compact dwarfs, it's as if a cosmic switch has been flipped, igniting a firestorm of creation that should, by all rights, tear the little galaxy apart. The energy and stellar winds pouring out from all these newborn stars are tremendous, and conventional logic suggests this should quickly blow away the remaining gas and dust, halting further star formation and disrupting the galaxy's delicate gravitational balance. Yet somehow, these systems not only hold together but often sustain these incredible bursts for surprisingly long periods. This apparent defiance of physics leads us to the heart of the mystery: dark matter. In the standard model of cosmology, all galaxies, large and small, are thought to be embedded within vast, massive halos of this invisible, mysterious substance. It is the gravitational glue of the universe, the unseen scaffolding that provides the extra mass needed to hold rapidly spinning galaxies together and prevent them from flying apart. The problem with the blue dwarfs inside the Small Magellanic Cloud is that their estimated visible mass is simply too small to account for their stability, especially given the violent astrophysical processes raging within them. The only plausible explanation is that they, too, must possess their own significant dark matter halos. This presents a fascinating and complex hierarchical puzzle. We have a large dark matter halo holding together the entire Small Magellanic Cloud, and within it, seemingly independent smaller dark matter halos holding together these frantic blue dwarfs. This challenges simpler models of galaxy formation that didn't predict such efficient and resilient small-scale structure within an already small galaxy. It suggests that the process of building galaxies, from the largest spirals to the tiniest dwarfs, is far more efficient and complex than we once believed, with dark matter organizing matter into stable clumps across a much wider range of scales. Studying these objects is incredibly difficult because their light often blends with that of their host galaxy, but their unique properties make them invaluable cosmic laboratories. Their chemically primitive environment, similar to the early universe, allows astronomers to study starburst processes in a more pristine setting, free from the complicating factors of heavier elements. By measuring the motions of stars and gas within these blue dwarfs, researchers can map the distribution of their unseen dark matter, providing crucial clues to its nature and behavior on the smallest galactic scales. Each of these brilliant blue knots is therefore a double puzzle, a question about the violent lives of stars and a profound question about the invisible fabric of the universe that makes their existence possible. Amidst the brilliant glow of star clusters and the vivid colors of emission nebulae, there lies a patch of profound darkness that is anything but empty. This is the dark nebula known as LHA 115N88, a cosmic inkblot that appears as a stark void against the tapestry of background stars. But this is no simple absence of light. It is a dense, cold cloud of gas and dust so thick that it completely blocks the stellar radiance behind it. What makes this particular dark nebula a subject of intense fascination is not just what it hides, but what it contains. Within its shadowy depths, astronomers have discovered a chemical treasure trove that is utterly unexpected for an object of its kind, challenging our understanding of where and how the building blocks of life can form in the universe. The most startling revelation about N88 is its surprisingly rich and complex composition. Using powerful radio telescopes that can peer through the obscuring dust, scientists have detected the spectroscopic fingerprints of numerous complex organic molecules, including long-chain carbon compounds and polycyclic aromatic hydrocarbons. These are essentially the large, complicated molecules that are the precursors to the amino acids and other compounds essential for life as we know it. Finding such a rich concentration of these prebiotic molecules in a relatively isolated dark nebula within a small, metal-poor galaxy like the Small Magellanic Cloud is completely counterintuitive. The prevailing wisdom had been that these intricate molecules required the richer chemical environment of larger galaxies to form efficiently. Their presence here suggests that the fundamental chemistry for life may be a far more common and universal process than we ever imagined, starting in the cold, dark nurseries between the stars long before planets ever form. Adding to the mystery is the nebula's bizarre physical structure. High-resolution images reveal that it is not a simple, amorphous blob of dust. Instead, it is crisscrossed by an intricate network of filamentary structures, delicate, thread-like tendrils that weave through the cloud like cosmic cobwebs. The origin of these filaments is a major puzzle. They could be the result of internal turbulence, where supersonic flows of gas within the cloud shear and stretch the material into these long, thin shapes. Alternatively, they might be shaped by external forces, such as the subtle but persistent pressure of radiation from nearby massive stars, slowly sculpting the cloud's outer layers. A more exotic possibility involves magnetic fields, which are known to channel material into flowing along field lines, potentially creating this intricate web-like appearance. Each of these mechanisms would leave a different signature in the motion and temperature of the gas, and astronomers are currently trying to untangle which force is the primary architect of this shadowy labyrinth. Perhaps the most confounding aspect of all is the contradictory data regarding the nebula's dynamics. When observed using certain methods that track the motions of specific molecules, parts of N88 appear to be undergoing gravitational collapse. Dense cores within the cloud seem to be pulling inward, potentially in the earliest stages of forming new stars, gathering mass from their surroundings in a slow, inexorable process. However, other observational techniques tell a completely different story, indicating that the outer layers of the nebula are actually expanding and dissipating, likely under the relentless pressure of stellar winds from brilliant young stars in the vicinity. This creates a bizarre and seemingly impossible situation where the cloud appears to be both collapsing and expanding at the very same time. This paradox forces astronomers to reconsider the simple, static pictures of these dark clouds. Instead, they are now viewed as incredibly dynamic entities with complex internal motions where different processes dominate in different regions simultaneously. It's a place of constant struggle between the inward pull of gravity and the outward push of radiation and stellar winds, a battle that will ultimately determine whether this dark nursery gives birth to new suns or is simply torn apart and scattered back into the interstellar medium. N88, in all its dark mystery, serves as a powerful reminder that the voids in our sky are often teeming with hidden activity. It challenges our assumptions about chemical enrichment, showing that the ingredients for life can emerge in the most unexpected places. Its complex structure reveals the subtle interplay of forces that shape the cosmos on the smallest scales, and its contradictory motions highlight the dynamic and ever-changing nature of even the darkest corners of space. This isn't just a cloud, it is a cosmic chemistry set and a physics laboratory, all wrapped in a cloak of darkness, urging us to look closer and question what we think we know about the birth of stars and the origins of life itself. Drifting within the faint tapestry of the Small Magellanic Cloud is a structure so vast and seemingly empty that it challenges our very perception of what a celestial object can be. This is DM74, a cosmic void known as a superbubble. Imagine a sphere of near-nothingness over 600 light-years across, a cavernous hollow carved out of the very fabric of the galaxy. Its dimensions are staggering. If placed in our own neighborhood, it would easily engulf the entire Orion Nebula and dozens of other star-forming regions, leaving a chilling sphere of darkness in its wake. These structures are not truly empty, of course, but are filled with a thin, searingly hot plasma that is invisible to optical telescopes. What we see instead is the spectacular glowing rim of the cavity, a wall of interstellar gas and dust that has been lit up and compressed by the immense forces that created this void. The very existence of a superbubble is a testament to the collective power of massive stars. The traditional explanation is that these caverns are sculpted over millions of years by the combined effects of powerful stellar winds from young, hot stars and the cataclysmic shockwaves from the supernova explosions that mark their violent deaths. It's a cosmic construction project driven by relentless destruction, where successive generations of stars work together to blow away the surrounding gas and create these enormous cavities. DM74, however, is not following the script. The first and most profound mystery is its astonishingly perfect spherical symmetry. In the chaotic and turbulent environment of a galaxy, such a flawless geometric shape is almost unheard of. Supernova explosions are inherently asymmetric events, and stellar winds can be variable and messy. For a bubble to maintain this pristine spherical form over such an immense volume of space suggests an orchestration of forces that is both incredibly powerful and remarkably uniform, a phenomenon that existing models of stellar feedback struggle to account for. This leads directly to the second and even deeper mystery, the ghost in the machine. To maintain its expansion against the pressure of the surrounding interstellar medium, a superbubble of this size requires a continuous and immense input of energy. Astronomers have therefore searched its center for the expected engine, a rich cluster of massive stars whose winds and eventual supernova would provide the necessary power. Yet, when they look to the heart of DM74, they find a profound absence. The central region is suspiciously, inexplicably empty of the luminous O-type stars or recent supernova remnants that should be there. It's as if we've arrived at the scene of a grand party to find a magnificently decorated ballroom still echoing with music, but all the guests have long since vanished without a trace. The energy source that carved this incredible structure and continues to push its boundaries outward has seemingly disappeared, leaving behind only the ghostly echo of its power. The enigma only deepens when we listen to the bubble rather than just look at it. Observations in the radio part of the spectrum have detected strange and powerful emissions originating from the expanding shell of the superbubble itself. These are not the standard radio waves we would expect from the gentle synchrotron radiation of electrons moving in magnetic fields, which is commonly seen in supernova remnants. Instead, the signal is anomalous, suggesting a much more energetic and poorly understood process is at work at the edges of this void. One compelling theory proposes that the shell of DM74 is acting as a gigantic particle accelerator. As the shock wave from the superbubbles expansion plows through the interstellar medium, it could theoretically accelerate protons and electrons to near light speed. When these ultra-relativistic particles then collide with the denser material in the shell, they would produce the very type of unusual radio emission that we detect. If confirmed, this would make the superbubble a natural and enormous version of human-made particle colliders, offering a unique laboratory to study high-energy physics on a truly cosmic scale. DM74 stands as a monumental cosmic paradox. It is a structure defined by its emptiness, yet it is teeming with unanswered questions. Its beautiful shape implies a powerful and ordered creation, yet the creator is missing. Its silent interior belies the furious activity detected at its edges. This ghostly superbubble forces astronomers to reconsider the life cycles of the most massive stars. Perhaps the central cluster did exist, but its stars have already lived their short, brilliant lives and died in supernova so long ago that their remnants have completely faded from view, leaving only the expanding bubble as their legacy. Or maybe our understanding of how energy is transferred from stars to their environment is fundamentally incomplete. Every new observation of this magnificent void brings us closer to understanding the powerful, invisible forces that shape galaxies from the inside out, reminding us that sometimes the most profound mysteries in the universe are not what is there, but what isn't. Yet even the ghostly, expanding void of DM74 cannot match the sheer stellar drama of a binary pair that has rewritten the rules of stellar behavior. Meet HD 5980, a system that is less like a pair of stars and more like two cosmic titans engaged in a perpetual, violent duel. Located within the vibrant star-forming region NGC 346, this binary system contains two of the most massive, luminous, and utterly unpredictable stars ever catalogued. For most of its history, it appeared as a fairly typical, though incredibly energetic, pair of massive stars. But then it erupted, and in doing so, temporarily became the single brightest stellar point in the entire Small Magellanic Cloud, captivating astronomers and challenging every model of stellar evolution we possess. The defining chapter in the saga of HD 5980 is the Great Eruption of 1994. Over a matter of weeks, the system's brightness began to surge inexplicably, increasing by a factor of more than 250. It wasn't a slow, steady climb. It was a violent, chaotic outburst that catapulted it to a luminosity millions of times greater than our Sun. For a brief, spectacular period, it outshone every other star in its host galaxy, mimicking the famous eruption of Eta Carinii in our own Milky Way over a century prior. This was not a supernova. The stars survived, but a colossal stellar tantrum that ejected an enormous amount of material into space at velocities exceeding 2,000 kilometers per second. The cause of this eruption remains one of the most heated debates in stellar astrophysics. The leading theory points to a phenomenon known as the line-driven instability, where the incredible radiation pressure from the star's surfaces becomes so intense that it overcomes gravity, literally blowing the star's outer layers off in a catastrophic, episodic event. What makes this system even more baffling are the strange chemical fingerprints left behind in the light from that eruption. Spectroscopic analysis revealed that the material violently ejected was not composed of the expected mix of hydrogen and helium. Instead, it was incredibly rich in nitrogen and helium and conspicuously poor in hydrogen and carbon. This peculiar composition is a direct window into the star's internal workings. It suggests that the eruption did not just scrape the surface. It dredged up material from deep within the stars, from layers where nuclear fusion had already processed the original hydrogen into helium and then into nitrogen. This is the exposed core of a star, violently revealed to the universe. Such a composition is the hallmark of a Wolf-Rayet star, a rare, advanced evolutionary stage for the most massive stars, where they have shed their outer envelopes to expose the burned-out elemental furnace within. The mystery is that HD 5980 seems to have reached this advanced, unstable stage while both stars are still very much alive and interacting, a scenario that standard stellar evolution models struggle to accommodate. Decades after its great outburst, HD 5980 continues to defy any simple classification. It exhibits characteristics of multiple, distinct types of massive stars simultaneously. It has the luminosity and powerful winds of a luminous blue variable, a class of hypergiant stars known for their dramatic mood swings and eruptions. It shows the nitrogen-rich spectrum of a Wolf-Rayet star, indicating advanced nuclear processing, and yet it remains locked in a tight, interacting binary orbit, a configuration that profoundly influences the evolution of both stars in ways we are only beginning to understand. The gravitational dance between them allows for mass transfer, tidal forces, and shared envelopes, creating a feedback loop of instability that single stars simply cannot experience. This system is a living laboratory for studying the most extreme phases of stellar life. It challenges the notion that stars evolve along a single, predictable path, instead presenting a far more dynamic and interactive story. By continuing to monitor its ongoing, powerful stellar winds and its occasional smaller outbursts, astronomers are piecing together a new narrative for the lives of the most massive stars, a story of violent transformation, elemental recycling, and a partnership so intense that it pushes both participants to the very brink of self-destruction. HD 5980 is a testament to the fact that in the cosmos, even the most fundamental rules are written in pencil, waiting for a brilliant, rebellious star to come along and erase them. But for all the stellar violence and luminous chaos we've witnessed, perhaps the most profound mystery in the Small Magellanic Cloud is something that isn't there at all, an object that, by all rights, should be glaringly obvious, yet remains stubbornly invisible. This is the case of the missing intermediate mass black hole. Lurking at the heart of several of the galaxy's densest and most ancient globular clusters, there should be a gravitational monster, a black hole of several thousand solar masses. We have the gravitational evidence that points to its presence. We see the tantalizing clues in flickering X-ray sources, but the object itself continues to evade direct detection, creating a paradox that challenges the very foundation of how we believe black holes form and grow. The search for these intermediate mass black holes, or IMB, is one of astronomy's most compelling detective stories. Unlike the stellar mass black holes formed from collapsing stars or the supermassive behemoths anchoring galaxies like our Milky Way, IMB represent a crucial missing link in the cosmic food chain. The prevailing theory suggests that the dense cores of ancient globular clusters are the perfect nurseries for them. In these stellar cities, where stars are packed millions of times more densely than in our solar neighborhood, chaotic gravitational interactions should inevitably cause smaller black holes to sink to the center, merge, and accumulate mass over billions of years, eventually forming a single, intermediate mass anchor. The Small Magellanic Cloud, with its population of pristine, old clusters, should be a prime hunting ground. Astronomers look for the telltale signs, stars orbiting an unseen point at impossibly high speeds, or a subtle but pervasive gravitational pull affecting the motions of countless stars in the cluster's core. In several clusters, the stellar motions are indeed perturbed in ways that strongly suggest a massive, invisible object is holding sway, a gravitational fingerprint pointing directly to a black hole of several thousand suns. The plot thickens with the discovery of mysterious, ultra-luminous X-ray sources, or ULCs, spotted on the peripheries of these same clusters. These are objects that pour out staggering amounts of high-energy radiation, far more than a typical stellar mass black hole could produce through accretion, yet not quite at the level of an active supermassive black hole. For a time, many astronomers believed these ULXs were the smoking gun, the intermediate mass black holes finally revealing themselves as they shred and consume stolen material from a companion star. However, upon closer inspection, a more nuanced and puzzling picture emerged. Some of these powerful X-ray sources were found to be wandering. They weren't sitting statically at the precise gravitational center of the cluster where the imp should reside. This has led to alternative theories suggesting some ULXs might actually be normal stellar mass black holes that are simply consuming matter at an extraordinarily high and unsustainable rate, creating the illusion of being more massive than they truly are. This absence is more than just a failed observation. It's a theoretical crisis. If these intermediate mass black holes are not forming in the ideal environments of globular clusters, then our entire understanding of black hole growth and hierarchical structure formation in the universe may be fundamentally flawed. It forces us to reconsider the violent dynamics within these clusters. Perhaps the very process that is supposed to build up an imp is also its own undoing. When black holes merge, the event sends powerful ripples through space-time called gravitational waves. This emission is not symmetric. It can give the resulting, larger black hole a powerful kick, propelling it at high velocity right out of the cluster entirely, ejecting the would-be monster into the galactic hinterlands before it can grow any further. Alternatively, in the cramped quarters of a cluster core, the gravitational slingshot effect might simply fling out the smaller black holes before they ever get a chance to merge and settle down, preventing the formation of a central anchor altogether. The hunt continues, with each new generation of telescopes bringing more sensitive instruments to bear on the problem. The search for the missing intermediate mass black hole is a pursuit that defines modern astronomy, a quest for an unseen object whose presence is inferred only through its subtle influence on the visible universe. Its eventual discovery or continued absence will force a profound rewrite of our cosmic textbooks, revealing whether the path to supermassive black holes is a direct chain of mergers or if the universe has other, more exotic methods for building the giants that lurk in the dark. While we search the cosmos for what we expect to find, some of the most incredible discoveries are the things we never knew to look for, objects that defy every known category. This brings us to a truly bizarre beacon shining in the infrared sky, an object known only by its catalog number, ERAS 00483-7347. Invisible light, it is utterly unremarkable, almost invisible. But when we shift our view to the infrared part of the spectrum, it becomes one of the single brightest objects in the entire Small Magellanic Cloud, blazing with a heat that is both intense and deeply mysterious. We are essentially looking at a cosmic forge, shrouded in an incredible thick cloak of its own making, and what that cloak is made of is just the first layer of a profound puzzle. The most immediate shock from spectroscopic analysis is the composition of the dust itself. The material surrounding this object isn't the typical, amorphous soot-like carbon grains commonly found around aging stars. Instead, it is rich in crystalline silicates, minerals like olivine and pyroxene, which are essentially the building blocks of rocks and planets. To find these compounds in such abundance and in such a pristine crystalline form is like finding a beach of perfectly formed sand crystals surrounding a volcano. The environment is far too violent and energetic for such orderly structures to normally exist. Crystallization requires a very specific set of conditions. Material must be heated to a precise high temperature and then cooled slowly and steadily to allow an orderly atomic lattice to form. The presence of so much crystalline dust suggests a history of dramatic, episodic heating and cooling events that we simply don't see in other dusty stellar objects, pointing to a uniquely violent and variable central engine. This immediately raises the central question: What incredible power source is lurking at the heart of this dusty shroud, capable of heating these grains to the extreme temperatures required to make them glow so brightly? The amount of energy being poured into the surrounding dust shell is staggering, and it must be coming from something truly extraordinary. The most logical suspect would be a massive star, but the object doesn't show the spectroscopic signatures of one. Another possibility is a recent supernova explosion, but there's no evidence of the expanding shock waves or elemental enrichment that such an event would leave behind. This has led theorists to some fascinating and exotic alternatives. Perhaps we are witnessing the final, furious death throes of a super-asymptotic giant branch star, a type of ultra-massive old star that is predicted to undergo a kind of super-wind phase, ejecting its entire envelope in a last gasp of immense power. Or maybe the engine is a binary system where a white dwarf star is steadily and violently stripping material from a bloated companion, creating a continuous furnace of friction and heat as the stolen matter spirals inward. The true significance of ERA's 00483-7347 may lie in its specific address. The fact that it is found in the low-metal environment of the Small Magellanic Cloud is likely the key to its entire existence. In a galaxy with fewer heavy elements, the rules of stellar physics change. Winds flowing from stars are less efficient, meaning massive stars can retain more of their mass throughout their lives. This altered mass loss can lead to entirely new and unforeseen evolutionary paths, creating strange hybrid objects that simply cannot form in richer, more polluted galaxies like our own. This infrared enigma might therefore represent a previously unknown stage of stellar evolution, a short-lived transitional phase that is unique to the primitive conditions of the early universe, a relic of how the first generations of stars might have died. It is a direct window into an alternate stellar reality, showing us that the universe has more ways for stars to live and die than we have yet dreamed of in our models. Amidst the chaotic beauty of stellar birth and the ghostly remnants of stellar death, the Small Magellanic Cloud holds a celestial object of such perfect, almost mathematical, symmetry that it feels deliberately crafted. This is SMP-28, a planetary nebula that stands apart not for its violence or its power, but for its impossible mirror image perfection. When viewed through powerful telescopes, it presents itself not as a chaotic cloud, but as two pristine, identical lobes of glowing gas, emerging from a central point like the wings of a cosmic butterfly. This breathtaking bipolar symmetry is so precise that it appears as if one side was created, and then simply folded over to form the other, a level of order that is profoundly rare in the naturally turbulent universe and points to a formation process of exquisite and unknown delicacy. The immediate puzzle for astronomers is how such flawless symmetry could even arise. The death of a star, which creates a planetary nebula, is typically a messy and complex event. As a star like our Sun nears the end of its life, it pulsates and throws off its outer layers in a series of fits and starts, often resulting in irregular, spherical, or mildly asymmetric shapes. For a nebula to form with such a perfectly balanced bipolar structure, the ejection of material must have been incredibly well organized and focused. The prevailing theory involves a central star that is not just dying but spinning at an immense rate. This rapid rotation, potentially combined with a powerful magnetic field, could act as a cosmic nozzle, channeling the outflowing gas into two narrow, opposing jets with incredible precision. However, the degree of symmetry in SMP-28 pushes this idea to its absolute limit, suggesting there are forces at work. Perhaps interactions with an unseen companion star or a previously unknown stability in the dying star's core that we have yet to fully comprehend. This initial mystery is eclipsed by an even deeper chemical conundrum. One would assume that an object so perfectly symmetrical in its shape would also be symmetrical in its composition. Yet, when astronomers used spectrographs to analyze the light from each of the twin lobes, they received a profound shock. The two sides are not identical twins, they are fraternal. One lobe shows a significantly higher abundance of certain elements, like nitrogen and helium, while its mirror image is richer in oxygen and hydrogen. This chemical asymmetry within a physically symmetric object is a direct contradiction that strikes at the heart of our models for how these nebulae form. The material in both lobes originated from the same star, so they should have the same chemical fingerprint. This imbalance suggests that the process of ejecting the stellar envelope was not a single, uniform event. Instead, it may have occurred in distinct phases, with material from different layers of the star's interior being funneled into each jet. Alternatively, the unseen companion star theorized to be shaping the nebula might itself be chemically peculiar, its own stellar wind polluting one of the outflow channels and altering its composition in a way that breaks the perfect mirror. At the heart of this symmetrical yet asymmetric wonder lies the engine of it all, the central star. This white dwarf remnant is the exposed, intensely hot core of the progenitor star, and it too is behaving in a way that defies easy classification. It pulses with a slow, steady rhythm, regularly increasing and decreasing in brightness. This in itself is not unusual. Many white dwarfs are variable stars. The problem is that its specific pulse period, the tempo of its brightening and dimming, doesn't match any known class of variable star. It's not following the established patterns of pulsating white dwarfs like ZZ Ceti stars, nor does it align with the behavior of other known variables. This unique rhythm suggests that the internal workings of this particular stellar remnant are unlike any we've studied before. Perhaps its pulsations are being driven by an unusual internal structure or a specific mix of elements in its atmosphere left over from its asymmetric death throes. Or maybe the gravitational tug of a close-orbiting companion star is periodically disturbing it, forcing it to beat to a drum that no single star could ever follow. SMP-28, in its beautiful contradiction, teaches us that even the most orderly appearances in the cosmos can hide profound disorder. Its perfect shape implies a controlled and precise death, while its chemical imbalance and erratic central heart reveal a far more complex and turbulent reality. It serves as a stunning reminder that the universe often presents us with a beautiful facade, challenging us to look deeper and discover the intricate and often contradictory mechanisms operating just beneath the surface. This twin nebula is a single object telling two different stories, and astronomers must now work to reconcile them into one. And now we turn our attention to a structure so vast it defies the scale of everything we've encountered so far, an object that isn't seen so much as heard, broadcasting its presence not in light, but in the silent whispers of radio waves. This is strange radio loop SMCS9, a celestial ring of incredible proportions. If you were to somehow place this loop in our own galactic neighborhood, it would dominate the night sky, appearing dozens of times larger than the full moon. Its most striking feature is its shape, a near-perfect, almost geometric circle of radio emission hanging in the void. In a universe dominated by chaotic, asymmetric forms, such a pristine circle feels almost unnatural, a cosmic signature that demands an explanation as elegant as its form. The first and most profound mystery of this loop is the sheer, staggering amount of energy required to create and sustain it. To illuminate such an enormous structure in radio wavelengths requires a power source of almost unimaginable violence. Astronomers have crunched the numbers, adding up the combined energy output of every known star, supernova remnant, and stellar wind within its bounds. The result is a definitive and puzzling shortfall. Even if all the available sources worked in perfect concert for millions of years, they still could not account for the energy shining from this single loop. It's as if we've found a brilliantly lit city in the desert, but our surveys show there's no power plant, no grid, and no fuel source large enough to keep the lights on. This energy deficit points to a single, cataclysmic event of unprecedented power, an explosion or release of energy so immense that it dwarfs our standard understanding of stellar death. This leads to the second layer of the enigma, the loop's strange silence across other wavelengths. When astronomers point optical telescopes toward it, they find mostly darkness. There is no corresponding shell of glowing gas that would typically mark a supernova blast wave. When X-ray telescopes scan the same region, they detect little to no emission from the million-degree plasma that should be there, heated by the immense shock of the expanding structure. This object is a radio phantom, a ghost that sings loudly in one part of the spectrum but remains utterly invisible in others. This selective visibility is a major clue. It suggests that the physical processes energizing the loop are uniquely tuned to accelerate electrons to high speeds in weak magnetic fields, which is precisely the mechanism that produces strong radio waves through synchrotron radiation, while generating very little visible light or X-rays. The environment within the loop appears to be both incredibly energetic and strangely cold and diffuse, a combination that challenges our existing playbook for classifying cosmic explosions. So what colossal event could have forged this perfect, energetic, yet invisible ring? The most compelling theory is that we are witnessing a previously unknown class of supernova remnant. Perhaps the progenitor star was a true behemoth, so massive that its explosion released energy on a scale we've never before measured, a type of hyper-supernova that is theorized but has never been conclusively observed. The perfect circular shape could be a clue that this explosion happened in a region of space that was unusually uniform and empty, allowing the shock wave to expand in a perfectly spherical manner without encountering dense clouds of gas that would warp its shape. Alternatively, the loop might not be a remnant at all, but an interstellar shock wave phenomenon on a galactic scale. It could be the aftermath of a titanic collision between two stellar winds from massive stars, or perhaps the expanding bubble from a densely packed star cluster whose collective winds have merged into a single, coherent structure. The true answer may be even more exotic. Some theorists have proposed that the loop is evidence of a failed gamma-ray burst, a beam of unbelievable energy that shot out from a collapsing star but was pointed away from our line of sight. We would not see the brilliant flash of the burst itself, but we would see the radio-emitting shock wave as it plowed into the interstellar medium and began to slow down, creating the perfect ring we observe today. Each of these possibilities pushes the boundaries of known astrophysics, suggesting that the death throes of stars can unfold in ways far more diverse and spectacular than our current models allow. Strange Radio Loop SMCS9 is more than just a curiosity. It is a profound question written across the sky, challenging us to expand our understanding of how the universe channels energy and marks the end of a star's life. Its perfect form is a silent testament to a violence so great and so focused that it momentarily imposed a stunning order upon the cosmic chaos. Yet even a structure as vast and energetic as that mysterious radio loop cannot outshine the raw, unpredictable brilliance of a single star that refuses to follow the rules. Our journey now takes us to one of the most luminous and temperamental objects in the entire Small Magellanic Cloud, the luminous blue variable star known as R40. This isn't just another massive star, it is a cosmic diva of the highest order, a stellar powerhouse whose dramatic and erratic performances defy every script written by astrophysicists. Classifying it as a luminous blue variable simply gives it a label it seems determined to rebel against, behaving in ways that make it a profound outlier even among its own notoriously unstable kin. The most immediate sign of its rebellion is its wild and utterly unpredictable brightness. A typical variable star, even a highly unstable one, usually follows some form of rhythmic pattern or cycle. Its changes in luminosity might be extreme, but they often occur over predictable timescales, allowing astronomers to forecast its behavior. R40, however, operates on pure chaos. It can languish at a relatively steady brightness for years, lulling observers into a false sense of security, only to suddenly plunge into a deep dimming event or erupt in a brilliant outburst without any discernible warning or cause. These swings are not minor fluctuations, they represent changes in energy output that are monumental in scale, suggesting profound and violent reorganizations are happening deep within the star's interior. It's as if the star possesses multiple personalities, each one taking control of the thermostat at random and turning it up or down to extremes that current models of stellar structure cannot account for. This internal turmoil manifests outwardly in the most spectacular fashion. Surrounding R40 are not one, but multiple concentric shells of gas and dust floating around the star like the layers of a cosmic onion. Each of these delicate structures is a fossilized record of the star's violent past, a ring of material violently ejected during a previous great outburst and then pushed outward by subsequent eruptions. By studying the expansion of these shells, astronomers can essentially carbon date these cataclysmic events, building a timeline of the star's epic tantrums. The very existence of multiple intact shells is itself a puzzle. Such structures should be disrupted and dissolved by the immense pressure of the star's own radiation and stellar wind, yet they persist, suggesting the ejection events are both incredibly violent and strangely cohesive, occurring in brief, focused outbursts that create these near-perfect expanding bubbles. Perhaps the deepest mystery lies in the star's reported surface temperature, which appears to fluctuate wildly in ways that directly contradict its changes in brightness. In standard stellar physics, luminosity and temperature are intimately linked. A star that grows brighter typically also grows hotter. Are Chinese letter DEFIES this fundamental relationship? There are periods where the star grows vastly brighter while its surface temperature appears to drop, and other times when it dims considerably while simultaneously heating up. This bizarre anti-correlation points to processes that are completely outside the scope of our current understanding. It suggests that the engine at the heart of R40 is not a simple, stable furnace. Instead, it may be prone to massive internal convulsions that temporarily alter how energy is generated and transported from the core to the surface. One leading theory proposes the existence of deep, powerful pulsations within the star that periodically push its opaque outer layers to incredible distances, creating a temporary, inflated photosphere that is both cooler and larger, thus appearing brighter even as its surface temperature drops. The extreme environment of the Small Magellanic Cloud is almost certainly a key player in this drama. The galaxy's low metallicity means its stars have weaker stellar winds. For a massive star like R40, this allows it to hold onto more of its mass throughout its life, becoming far heavier and more unstable than a comparable star in our metal-rich Milky Way could ever be. It may represent a living relic of how the first generation of supermassive stars in the early universe behaved, stars that were so massive and volatile that they lived short, spectacular lives defined by colossal eruptions before ending their lives in hypernova that seeded the cosmos with its first heavy elements. R40 is more than just a misbehaving star. It is a window into a more violent and extreme chapter of cosmic history, a lone actor on a galactic stage performing a play whose script we are only beginning to decipher. Nestled within the gravitational embrace of the Small Magellanic Cloud lies a celestial artifact so ancient it predates most of the galaxy itself, the globular cluster NGC 419. From a distance, it presents a classic picture, a dense spherical swarm of hundreds of thousands of stars bound together by gravity for billions of years. It should be a simple, pristine relic from the early universe, a single burst of star formation frozen in time. But when astronomers peer deeper into its heart, they find a paradox that shatters the textbook definition of what a globular cluster can be. This is not a simple, single-generation family of stars. It is a complex stellar society with a layered and impossible history, a discovery that has forced a complete rethinking of how these cosmic fossils are born and live. The most profound and immediately baffling discovery about NGC 419 is the clear, undeniable presence of multiple distinct populations of stars within it. In a standard globular cluster, every star is born from the same primordial cloud of gas at essentially the same time. They should all be the same age, like twins born from the same pregnancy. Yet, detailed observations from telescopes like Hubble reveal that the stars in NGC 419 are not all identical. Their colors and brightnesses tell a story of a significant age spread. While the vast majority of its stars are indeed ancient, around 11 to 12 billion years old, a substantial fraction of them appear to be noticeably younger by perhaps 1 to 2 billion years. This is not a minor discrepancy. It's a fundamental violation of the long-held rule that globular clusters are simple, single-age stellar systems. It suggests that this cluster did not form all its stars in one grand explosive event. Instead, it somehow managed to hold onto enough gas after its initial birth to fuel a second, and perhaps even a third, major epoch of star formation billions of years later. This is a behavior astronomers expected to see in much larger dwarf galaxies, not inside a tightly bound globular cluster whose fierce stellar winds and supernova explosions should have blown all its remaining gas away immediately. This mystery of multiple births is compounded by a second, equally strange chemical signature. As stars die, they seed their surroundings with heavier elements forged in their cores, elements like oxygen, sodium, and aluminum. In a typical cluster, this chemically enriched material is lost forever, blown into the vast interstellar medium. But in NGC 419, the younger generations of stars are chemically distinct from the older ones. They show enhanced levels of certain elements, particularly nitrogen. This is the smoking gun. It means that the gas that formed these younger stars wasn't pristine. It had been polluted by the ashes of the previous generation. The cluster somehow managed to retain this enriched material, cool it down, and recycle it into a new wave of star formation, all while maintaining its gravitational integrity. It's as if a city not only sustained its population for billions of years, but also managed to use its own waste and industrial byproducts as the raw materials to build new, more advanced districts, all within the original city limits. Perhaps the most disorienting quality of NGC 419 is its schizophrenic structure, which seems to defy its own advanced age. Ancient globular clusters are expected to undergo a process called core collapse, where their most massive stars sink to the center through gravitational interactions over billions of years, creating an incredibly dense, bright core. Yet, NGC 419, for all its immense age, shows no sign of this. Its core remains relatively loose and puffy, a structural feature more commonly associated with young, dynamically adolescent clusters that haven't had time to settle. At the same time, it possesses a rich and well-developed family of millisecond pulsars, old neutron stars, spun up to incredible speeds by absorbing material from a companion. These are objects that require billions of years to form, proving the cluster is indeed ancient. So we are left with a cosmic contradiction, a cluster that has the internal dynamics of a youthful system, but the stellar inhabitants of a profoundly old one. It's like meeting a person who has the vibrant energy and appearance of a 20-year-old but carries a passport confirming they were born in ancient Rome. The existence of NGC 419 forces astronomers to consider radical new ideas about globular cluster formation. Perhaps it was not always the dense sphere we see today. Maybe it began its life as a much larger and more massive structure, a dwarf galaxy nucleus or a gigantic stellar nursery that was mostly stripped away by tidal forces, leaving behind only its dense, complex core, the NGC 419 we observe now. This would explain its ability to hold onto gas, its original gravitational well would have been far deeper, allowing it to weather the storms of early supernova. Its peculiar structure could then be a frozen relic of that more massive past, a ghost of a greater galaxy that refuses to conform to the evolution of a normal cluster. Every observation of this ancient enigma peels back another layer, revealing a story of cosmic life that is far more complex, resilient, and interconnected than we ever believed possible. Flowing through the cosmic tides alongside the Small Magellanic Cloud is a ghost, a celestial specter whose presence is felt not by the light it emits, but by the profound gravity it exerts. This is the ultra-faint dwarf galaxy known as Small Magellanic, an object so ethereal it barely qualifies as a galaxy in the traditional sense. If you were to point the most powerful optical telescope at its coordinates, you would see almost nothing, a scant handful of stars so faint and widely spaced they appear as lonely, forgotten sentinels in the void. Its total luminosity is less than that of a single bright giant star in our own galaxy. Yet, for all its apparent emptiness, measurements of the motions of those few visible stars reveal a shocking truth. This phantom is immensely heavy. The tiny number of stars we can see are moving at velocities that are far too high, whipping around as if held in the grip of a gravitational anchor of staggering proportions. The inescapable conclusion is that Small Magellanic is not mostly empty space, it is mostly dark matter. This presents an immediate and profound paradox. Small Magellanic is located exceptionally close to the much larger Small Magellanic Cloud, well within what should be its destructive gravitational influence. According to our established models of galactic interactions, the immense tidal forces from a larger neighbor should have ripped a small, diffuse system like this apart eons ago, stretching its stars and its dark matter halo into a long, dissolving stream within the larger galaxy's orbit. The fact that Small Magellanic remains intact, a distinct and coherent gravitational entity, suggests that its dark matter halo is not just massive, but possesses a unique and unexpected property. It must be incredibly dense and tightly bound, forming a concentrated, resilient core of invisible matter that can withstand the relentless pulling and shearing forces that have shredded other similar objects. This resilience implies that dark matter might not be as smooth and featureless as some theories suggest, but can instead clump and condense into extremely dense knots on surprisingly small scales, acting as a kind of unshakable gravitational skeleton that holds the ghost galaxy together against all odds. The existence of such a dark matter-dominated fossil has monumental implications for our understanding of the universe's fundamental structure. Small Magellanic is not an anomaly. It is likely a prototype, a pristine example of the most common type of galaxy in the entire cosmos. Theories of dark matter predict that the universe should be teeming with countless such ultra-faint dwarfs, the leftover building blocks from which larger galaxies like our own were assembled. The fact that we have such difficulty finding them because they emit almost no light creates what astronomers call the missing satellites problem. Small Magellanic is one of the few we have actually found, a crucial piece of observational evidence that these dark matter halos do indeed exist and can survive for billions of years. Its very presence helps to validate the entire cold dark matter model of cosmology, proving that dark matter can form stable structures on the scale of small galaxies. Yet, for all the answers it provides, Small Magellanic poses an even deeper question about the nature of star formation itself. With such an immense reservoir of mass in its dark matter halo, why did so few stars ever form here? The conditions seem perfect, plenty of gravitational pull to gather gas, and presumably a supply of primordial hydrogen and helium from the early universe. The answer may lie in its ancient, pristine environment. Perhaps the gas that was initially drawn into the halo was simply too pure, lacking the heavy elements and dust grains that act as cooling agents and catalysts for star formation. Without these metals, the gas could not efficiently radiate away its heat, preventing it from collapsing into dense enough clouds to ignite new stars. Or maybe the small galaxy experienced a single, brief burst of star formation that quickly blew away the remaining gas with the stellar winds and radiation from its firstborn stars, shutting down the process forever and leaving Nod frozen in time as a mostly dark relic. This object is more than just a galaxy. It is a cosmic fossil, a preserved snapshot of a time when dark matter ruled alone, and the first lights of the universe were only just beginning to flicker hesitantly against the immense, overwhelming dark. But for every ancient, dark matter-dominated relic, there is a place of spectacular, brilliant birth, and few places in the local universe embody this more than the sprawling stellar nursery known as N66. This isn't just another nebula. It is the largest and most complex region of ionized hydrogen gas in the entire Small Magellanic Cloud, a seething cauldron of creation where the rules of star formation are being rewritten in real time. At first glance, it presents a breathtaking tapestry of light and shadow, with brilliant knots of newly ignited stars set against mysterious, intricate dark lanes that wind through the glowing gas like cosmic rivers of ink. This beautiful chaos, however, is merely the surface of a far deeper mystery, one that challenges our fundamental understanding of how stars are born. The first clue that N66 is behaving strangely comes from the very stars it has created. In a typical giant H2 region, like the famed Orion Nebula in our Milky Way, the most massive and luminous stars are predictably found at the heart of the brightest gas clouds, their fierce radiation and powerful winds carving out cavities around them. But here, the distribution is bizarrely inverted. Some of the youngest and most massive stars are not in the center. They are scattered around the periphery of the nebula, as if they were flung outward from the main event. This unexpected arrangement suggests that star formation in N66 did not begin with a single collapse. Instead, it appears to be the result of a titanic collision between multiple, massive clouds of interstellar gas. As these vast structures slammed into one another, they created shock waves that rippled through the material, triggering frantic bursts of star formation at the points of impact and along the expanding fronts of the collision, rather than in one centralized location. It's a top-down, chaotic process, a stark contrast to the more orderly, gravity-led collapse we are used to seeing. This theory of colliding clouds is dramatically confirmed when astronomers measure the velocity of the gas itself. Using sophisticated spectrographs, they have mapped the movements within N66 and discovered a mind-bogglingly complex velocity structure. The nebula is not expanding or rotating in a simple, unified way. Instead, it is a roiling maelstrom of different gas streams, all flowing in contradictory directions at speeds of dozens of kilometers per second. Some filaments are rushing toward us while others are speeding away, and still others are moving tangentially, creating a turbulent, three-dimensional ballet. This is the unmistakable signature of a system that has not yet settled into equilibrium after a violent and energetic origin event. We are essentially witnessing the aftermath of a cosmic car crash, with the wreckage of multiple gas clouds now mixing together and igniting new stars in the fiery aftermath. Within this turbulent environment, perhaps the most tantalizing discoveries are the proplyds, or protoplanetary disks. These are dense, spinning disks of gas and dust encircling infant stars, the very raw material from which planets are built. We've found them in abundance in our own galactic neighborhood, but in N66 they appear to be evolving under a different set of rules. The intense, harsh radiation from the many massive stars nearby is proving to be a double-edged sword. On one hand, this radiation is so powerful that it is actively evaporating these fragile disks, stripping away their material and potentially limiting the amount of mass available to form planets. We can actually see this process happening, with the proplyds sporting comet-like tails of material being blown away by the stellar winds. Yet, paradoxically, this same destructive radiation might also be a catalyst for creation. The immense external pressure from the radiation and stellar winds could actually be compressing the outer parts of these disks, accelerating the process of grain growth and pebble formation, the very first steps in building planets. It's a dramatic race against time. Can planets form fast enough within these disks before they are completely blown away? The low metal environment of the Small Magellanic Cloud adds another fascinating layer to this puzzle. With less dust to absorb and shield against the radiation, the proplyds here might be more vulnerable, yet they might also foster the formation of rocky planetary cores through different physical processes. N66 is therefore a natural laboratory, showing us that the path to planet formation is not a single, universal recipe, but a diverse set of possibilities heavily influenced by a star's violent and nurturing birthplace. Streaking through the sparse interstellar medium of the Small Magellanic Cloud is a cosmic cannonball, a stellar remnant on a one-way trip into the void. This is the pulsar known as PSRJ 0045-7319, a neutron star that has been violently ejected from its birthplace and is now traveling at hundreds of kilometers per second. Its very existence is a relic of a catastrophic stellar divorce, a story written in its incredible speed and the enigmatic wake it leaves behind. To understand this runaway pulsar is to piece together a dramatic history of gravitational betrayal and explosive force, an event that forever altered its trajectory and continues to challenge our models of how these dense objects behave. The most widely accepted origin story for this celestial fugitive begins with a binary star system, a pair of massive stars locked in a mutual gravitational dance. The more massive of the two would have lived its life quickly, burning through its nuclear fuel in a few million years before its core collapsed, resulting in a supernova explosion. In a tightly bound binary pair, such an explosion is never a quiet affair. It is a profoundly asymmetric event. If the collapsing star ejects its outer layers in one direction more powerfully than another, the newborn neutron star at its core can receive a tremendous kick in the opposite direction, like a rocket firing off its launch pad. This natal kick, combined with the sudden loss of the exploding star's gravitational pull, can be more than enough to fling the neutron star clear of the system entirely, sending it careening through space on a new, solitary path. PSRJ 0045-7319 is the product of just such a violent birth, a child cast out from its home by the very explosion that created it. As this ultra-fast neutron star plows through the tenuous gas that fills the space between stars, it does not move unnoticed. Its powerful magnetic field, trillions of times stronger than Earth's, and the intense wind of high-energy particles streaming from its surface act like the bow of a ship cutting through water. They push against the interstellar medium, compressing and heating the gas ahead of it into a luminous shock wave. This structure, known as a bow shock, typically glows in the visible light of hydrogen alpha, creating a ghostly, arcing veil in front of the pulsar. However, this particular bow shock refuses to follow the standard script. While it does emit some visible light, it is also an unexpectedly bright source of X-ray emission. This is highly unusual, as the velocities involved in these shocks are typically not sufficient to heat the gas to the millions of degrees required to produce such high-energy radiation. The presence of this strong X-ray glow suggests there are far more energetic processes at work within the shock than our current models predict, perhaps involving the pulsar's intense magnetic field channeling and accelerating particles to near light speed before they slam into the interstellar gas. Perhaps the most persistent puzzle surrounding this object is the contradiction between its estimated age and its current behavior. We can estimate how long ago the supernova explosion that created it occurred by tracing its path backwards to a likely birthplace, such as a young star cluster. We can also estimate its age by measuring its spin-down rate. Pulsars are born spinning rapidly, and over millions of years, they gradually slow down as they lose rotational energy to their powerful winds and magnetic fields. By measuring how quickly its spin is slowing, astronomers can calculate a characteristic age, For most pulsars, these two ages align reasonably well. For this runaway pulsar, they tell two completely different stories. Its kinematic age, based on its speed and trajectory, suggests it is a relatively young object. Its spin-down age, however, suggests it is significantly older. This discrepancy points to a gap in our understanding of pulsar physics. It's possible that the standard spin-down model is too simple, and that a pulsar's braking mechanism can be influenced by other factors we haven't accounted for, such as the dense environment of its birth or the specific conditions of its ejection. Alternatively, the pulsar's rapid motion through space might itself be affecting how it interacts with the surrounding medium, subtly altering the way it loses rotational energy and throwing off our traditional calculations. This runaway object is more than just a fascinating speedster. It is a natural experiment, forcing us to refine our theories and acknowledge that the life of a neutron star is even more complex and dynamic than we once believed. Yet for all the drama of runaway pulsars and colliding gas clouds, few objects in the Small Magellanic Cloud embody sheer, unpredictable power quite like SMC X3. This isn't just another X-ray binary, it is a cosmic pressure cooker whose lid seems to blow off at random, flooding detectors with high-energy radiation in outbursts that defy all prediction. At its heart lies a neutron star, a gravitational vampire locked in orbit with a massive companion. But unlike the steady, rhythmic feeding of other systems, the activity here is chaotic, erupting into violent, luminous tantrums that have left astronomers scrambling for an explanation. The very timing of these eruptions is the first major clue that something is deeply unusual here, pointing to a companion star unlike any we've seen before. The most baffling aspect of SMC X3 is the bizarre disconnect between its orbital period and its outburst schedule. In a typical X-ray binary, the neutron star's feeding frenzy is dictated by its orbit. As it swings closer to its companion, its gravity pulls a stream of material away, leading to a predictable spike in X-rays. SMC X3 follows no such rule. Its orbit is a steady 45-day loop, but its monstrous X-ray outbursts during which its brightness can increase by a factor of 10,000 occur on a wildly irregular timetable. They can happen at any point in the orbital dance, sometimes when the two stars are at their farthest separation, a time when accretion should be at its absolute minimum. This fundamental disconnect suggests that the flow of material onto the neutron star is not being governed by simple gravity alone. Something else, something hidden within the companion star itself, is dictating the tempo of this violent relationship, turning the accretion process on and off like a faulty tap. This strange behavior forces a radical rethinking of the companion star's identity. To fuel such powerful and irregular outbursts, this must be no ordinary star. The prevailing theory suggests we are looking at a B star, a type of hot, massive star known for its rapid rotation and a surrounding decretion disk of its own ejected material. But this cannot be a standard B star. The scale and violence of the outbursts imply a disk of incredible density and stability, one that persists for long periods before suddenly destabilizing and dumping a colossal amount of mass onto the waiting neutron star all at once. This points to a companion that is spinning at the very brink of its own destruction, rotating so fast it is nearly flinging itself apart, maintaining a vast reservoir of material in a precarious balance that occasionally tips over the edge. It may represent a previously unknown evolutionary stage for such stars, a short-lived and hyperactive phase that we are only now discovering because of the spectacular fireworks it triggers. When the outbursts do occur, the resulting X-ray spectrum is a complex mess of contradictions that reveals the sheer chaos of the accretion process. The light is not a clean signal. It is a forest of emission and absorption lines, telling a story of material crashing onto the neutron star's surface at a furious, chaotic rate. The spectra show clear signs of what astronomers call a photoionized plasma. This means the insane amount of X-rays pouring from the neutron star is so intense that it is literally stripping electrons from the atoms in the incoming stream of gas before they even have a chance to accrete, creating a superheated, magnetically confined shroud around the pulsar. We are not seeing the clean impact of gas on a solid surface. We are witnessing a turbulent, radiating atmosphere that forms and dissipates with the raging flow of material, a dynamic and complex environment that is incredibly difficult to model. The final piece of this puzzle may lie in the powerful magnetic field of the neutron star itself, which is estimated to be trillions of times stronger than Earth. In most such systems, the magnetic field acts as a funnel, neatly directing incoming material to the magnetic poles. In SMC X3, the sheer volume of material being transferred during an outburst might be so immense that it temporarily overwhelms this magnetic funnel. The field could become buried or distorted by the flood of gas, leading to a period of chaotic, spherical accretion before it can reassert control and re-establish the orderly columns that produce the clean, pulsating X-ray signal we expect. This constant battle for dominance between the neutron star's magnetic fury and the companion star's overwhelming generosity creates the unpredictable and spectacularly violent behavior that makes SMC X3 a unique laboratory for studying the absolute limits of accretion physics. While the violent tantrums of SMC X3 showcase the chaos of accretion, the Small Magellanic Cloud holds a mystery that is its absolute opposite. An object defined not by what it reveals, but by what it conceals. This is the infrared ghost, officially catalogued as BI 7748, a celestial spectre that is utterly invisible to our eyes and optical telescopes, yet blazes with an intense and puzzling light in the infrared part of the spectrum. It has no optical counterpart whatsoever. If you were to point the most powerful visible light telescope at its coordinates, you would see only the empty black of space, a perfect void. But switch to an infrared view and a brilliant beacon appears, shining with a heat signature that is both powerful and deeply strange, a true phantom of the cosmic depths. The most immediate clue to its nature is its extreme color, or more accurately, its incredible redness in the infrared. All objects emit radiation across a range of wavelengths, and the specific pattern of that emission acts like a thermal fingerprint, telling us about the object's temperature and composition. BI 7748 is among the reddest objects ever detected, meaning its light is heavily skewed toward the longest, least energetic infrared wavelength. This profound redness suggests one of two fascinating possibilities. The first is that we are looking at something extremely cold, an object or cloud of material with a temperature of only a few hundred degrees above absolute zero. At such frigid temperatures, it would naturally glow only in the far infrared, much like a piece of iron that hasn't yet been heated enough to glow red to our eyes. The second and more intriguing possibility is that we are not seeing an object's temperature at all, but rather the unique signature of its dust. The extreme redness could be caused by a shroud of dust grains that are unusually large or have a highly exotic chemical composition, grains that are extraordinarily efficient at absorbing shorter wavelength light and re-radiating it only at these very long red infrared wavelengths. This wouldn't be the common soot-like carbon dust we often find. It would be something new and different. This ghost, however, is not a static entity. Adding a profound layer of mystery is the fact that its infrared brightness does not remain constant. It varies, fluctuating in intensity over irregular and unpredictable timescales. This variability is the key piece of evidence that tells us we are not just looking at a passive, cold cloud of dust. Something dynamic and energetic is happening at its heart, a power source that is turning on and off or changing in intensity. The irregular timing of these changes rules out simple, rhythmic processes like the rotation of a solid body or the orbit of a binary pair. Instead, it points to something far more chaotic, perhaps episodic outbursts from a central engine, where material is dumped onto a hidden source in violent, irregular bursts, heating the surrounding dust shell and causing the entire system to brighten temporarily before fading again. The true identity of this central engine is the core of the mystery. It must be powerful enough to heat a substantial dust shell to the point that it glows brightly in the infrared, yet be completely hidden from our view at all other wavelengths. This suggests the dust shroud surrounding it is incredibly thick and uniform, a nearly perfect cocoon that allows no visible light to escape. The most plausible suspects are stellar objects in extreme transitional phases of their lives. It could be a massive star that has recently experienced a tremendous eruption, similar to the Great Eruption of Eta Carinii, ejecting a vast amount of material that has now cooled into an opaque dust shell, temporarily hiding the star from view. Alternatively, it might be a protoplanetary nebula, a short-lived phase where a dying star has puffed off its outer layers, but its exposed core has not yet heated enough to ionize the ejected gas and make it glow. During this brief period, the only signature is the warm glow of the dust. The possibility that is most exciting to astronomers is that BI 7748 does not fit neatly into any of these known categories. Its combination of extreme redness, total optical invisibility, and irregular variability might signify something entirely new, a previously unrecognized class of astronomical object. And its location in the low metallicity environment of the Small Magellanic Cloud could be the reason we haven't seen it before. In a galaxy lacking heavy elements, the process of dust formation is different. Stars can hold onto their mass longer, leading to more extreme eruptions, and the dust grains that form can have different sizes and compositions. This object may therefore be a unique product of its primitive environment, a rare and short-lived stage of stellar evolution that is only possible in conditions mimicking the early universe. The infrared ghost is more than just a hidden object. It is a potential window into an alternate pathway of stellar life and death, a faint, warm whisper from the dark that hints at the diversity of cosmic phenomena still waiting to be discovered. Nestled within the tapestry of the Small Magellanic Cloud is an open star cluster that presents a paradox as profound as any we've encountered. Designated Lindsay 113, this collection of stars should be a straightforward family portrait, a group of siblings all born from the same primordial cloud of gas at roughly the same time. They should share the same age and a similar chemical composition, a single chapter in the galaxy's history. Yet, when astronomers analyze this cluster in detail, they find a story that is deeply fractured and seemingly impossible, a celestial puzzle that challenges the most fundamental principles of stellar genealogy. The most immediate and baffling discovery is the cluster's impossible age spread. Through precise measurements of the star's colors and brightnesses, a technique that allows astronomers to accurately estimate their ages, researchers found that the stars in Lindsay 113 are not contemporaries. A significant portion of them appear to be roughly 1 to 2 billion years older than the rest. This isn't a minor measurement error, it's a chasm in time that defies all logic. In a gravitationally bound open cluster, all stars form together in a single, concerted collapse event that typically lasts only a few million years. The idea that the same cloud of gas could somehow pause its star formation for over a billion years and then start again, all while holding itself together against the disruptive tides of the galaxy, is a scenario that no standard model of cluster formation can explain. It suggests this cluster has a resilience and a history far more complex than its modest appearance would imply. The plot thickens considerably when we examine the chemical fingerprints of these stars. Spectroscopic analysis reveals that the older stellar population within the cluster possesses a distinctly different chemical signature than their younger siblings. Their atmospheres are enriched with specific elements, particularly iron peak elements, in a way that the younger stars are not. This is the crucial clue that points to an external culprit. Stars inherit their chemical composition directly from the cloud they form from. If both generations had formed from the same original cloud, they would be chemically identical. The fact that they are not means that the raw material that formed the second wave of stars was not the cluster's original gas. It had been polluted, enriched by an outside source. Something happened long after the cluster's initial birth that delivered a fresh infusion of chemically processed material into the cluster's heart, providing the fuel for a second epoch of star formation. This leads to the thrilling detective work of identifying the source of this contamination. The prime suspect is a traveling stellar assassin, a supernova from a passing star that did not belong to the cluster itself. Imagine Lindsay 113 drifting through the galaxy, its initial star formation complete. Millions of years later, a massive rogue star on its own solitary path happens to venture nearby. This star lives its short, violent life and ends in a supernova explosion, hurling its elemental ashes across space. Some of this enriched debris, traveling at incredible speeds, could have slammed into the dormant gas cloud still lingering within Lindsay 113. This sudden injection of heavy elements and kinetic energy would have shock-compressed the cloud, simultaneously polluting it and triggering the collapse that led to the new, younger generation of stars. It's a story of cosmic serendipity and violence where a distant death gives birth to new life. The final piece of this mystery is written in the stars' positions. In a typical cluster, dynamical evolution over time causes the most massive stars to sink toward the center through gravitational interactions. In Lindsay 113, this expected sorting has not occurred. The spatial distribution of stars shows no clear correlation with their mass or, more puzzlingly, with their age. The older and younger stars are thoroughly mingled, as if the second generation formed right in the heart of the first without any of the dynamical settling that billions of years of orbital interactions should have caused. This strange distribution suggests that the second infall of gas was not a gentle rain. It was a direct, focused accretion event that delivered new material right into the cluster's core, allowing new stars to form deeply embedded within the gravitational well of their older siblings from the very beginning. Lindsay 113 stands as a stunning counterexample to the idea of clusters as simple, isolated systems. It appears to be a cluster that has lived two lives, its history shaped by a dramatic encounter with the wider galaxy. It forces astronomers to consider star clusters not as closed islands, but as open systems that can capture material and be influenced by events far beyond their borders. This one unassuming cluster teaches us that the story of star formation is not always a local affair. Sometimes it's a tale written across vast distances, connecting the death of one star to the birth of another in a cycle of cosmic inheritance. Amidst the fiery reds and soft pinks that dominate the nebula palette of the Small Magellanic Cloud, one glowing cloud stands out with a curiously cool and verdant hue. This is Anomalies 99, an emission nebula that has earned the nickname the Green Nebula for its striking coloration when viewed through specific optical filters. While not green to the naked eye in the same way a planet might appear, its unique spectral signature emphasizes this particular shade, setting it apart from the typical hydrogen alpha red that paints most stellar nurseries. This unusual color is our first clue that we are looking at an object with a fundamentally different set of rules governing its existence, a cosmic outlier whose light tells a story of unique chemistry and a hidden power source. The secret to its unusual green glow lies not in the common process that lights most nebulae, but in a specific and rarefied ionization state. The predominant green emission comes from doubly ionized oxygen, denoted as O3. For an oxygen atom to be stripped of 2 electrons requires a very precise and powerful source of ultraviolet radiation, typically the domain of extremely hot, massive O-type stars. This high-energy light excites the oxygen atoms, and when they recapture electrons and return to a lower energy state, they emit light at specific wavelengths that our instruments and processed images interpret as a vivid green. It's a delicate balancing act. The radiation source must be powerful enough to achieve this double ionization, yet not so harsh that it completely blows the nebula apart or strips away even more electrons, which would change the emitted light. This perfect, fragile equilibrium is what gives Hennies 99 its distinctive and beautiful color. This immediately presents a profound mystery. To produce the copious amounts of ultraviolet radiation needed to create and sustain this O3 glow, there should be one or more tremendously massive, hot stars at the nebula's heart. These stellar power plants are usually impossible to miss, blazing with the blue-white intensity of a stellar titan. Yet, when astronomers search the core of Hennies 99, they find a profound absence. No suitably massive stars are present. It's as if we've found a brilliantly lit room with no visible light bulb. The energy is clearly there, pouring out to illuminate the gas, but the source itself is hidden, invalidating the most straightforward explanation and forcing a search for more exotic alternatives. One compelling theory suggests that the primary ionizing source may not be a single star, but a dense cluster of lower mass hot stars whose combined ultraviolet output is enough to do the job. Individually, these stars might be too faint to easily detect against the bright backdrop of the nebula itself, but together, their cumulative radiation could provide the necessary power. Another, more intriguing possibility involves a stellar corpse, a white dwarf or a neutron star left behind by a supernova that has since faded from view. Such a remnant could still be accreting material from a faint companion or from the nebula itself, generating intense X-rays and high-energy radiation that could effectively ionize the surrounding oxygen. A third hypothesis points to a phenomenon known as a leaky H2 region, where the ultraviolet photons from massive stars located far outside the nebula itself have managed to travel great distances through the low-density environment of the Small Magellanic Cloud to ionize Hennies 99. Each of these explanations challenges our conventional understanding of how these beautiful structures form and are maintained. The puzzle deepens when we examine the nebula's chemical composition. Spectroscopic analysis reveals that Hennies 99 has a significantly lower abundance of heavier elements, what astronomers call metals, compared to similar green-tinged nebulae in our own Milky Way. This is a direct consequence of its location in the Small Magellanic Cloud, a galaxy known for its primitive, low-metal environment. This lack of metals changes the physics within the nebula in crucial ways. With fewer heavy elements acting as cooling agents, the gas within Hennies 99 cannot radiate away its heat as efficiently. This results in a hotter, more turbulent internal environment where the processes of ionization and recombination play out differently than they would in a richer galaxy. The lower dust content also means that the destructive ultraviolet radiation can penetrate deeper into the cloud, potentially creating larger zones of double ionized oxygen and enhancing the green glow we observe. Hennies 99, in its serene and mysterious green light, is far more than a celestial curiosity. It is a natural laboratory for studying astrophysical processes under conditions that are increasingly rare in our own metal-enriched galactic neighborhood. Its missing engine forces us to consider collective and hidden sources of energy, while its unique composition shows us how the primordial building blocks of the universe behave when left to their own devices. This nebula is a beautiful exception, a reminder that for every rule we write about the cosmos, there is often a faint green ember in the dark ready to prove us wrong. But as we search for answers in the swirling chaos of nebulae and the quiet darkness of ancient clusters, we now turn our attention to a single, unassuming point of light that may be the most bizarre object of all, a star that should not exist. This is HV 2112, a variable star whose faint flicker hides a secret so profound it could rewrite the final chapters of stellar evolution. At first glance, it appears as just one among thousands of variable stars in the Small Magellanic Cloud, but its light, when split into a spectrum, tells a story that is utterly extraordinary. The chemical fingerprints revealed in that light point to processes so rare and extreme that they have led some astronomers to propose a truly mind-bending possibility. We may be looking at a cosmic Russian nesting doll, a star within a star, known theoretically as a Thorne-Zitkow object. The concept of a Thorne-Zitkow object sounds like pure science fiction, a theoretical endpoint for stellar evolution dreamed up by physicists Kip Thorne and Anna Zitkow in the 1970s. They proposed that under very specific and violent circumstances, a super-dense neutron star could be engulfed by a massive, bloated red supergiant star. Instead of being consumed or causing an immediate explosion, the neutron star would survive, sinking down to the core of its gigantic host. There, it would continue to orbit, acting as a bizarre, ultra-hot engine at the heart of the larger star. This isn't a binary system where two stars orbit each other at a distance. This is a single star with a neutron star as its core, a configuration that would create an entirely new and unique type of celestial object with properties unlike anything else in the universe. The evidence for this incredible idea comes from the very specific chemical soup detected on the surface of HV 2112. The star's atmosphere is astonishingly rich in exotic heavy elements like rubidium, lithium, molybdenum, and gallium. These are not elements forged in the typical nuclear fusion processes of a star's core. Instead, they are the products of a rare and slow process called neutron capture, where atomic nuclei slowly absorb neutrons one at a time, building themselves into heavier and heavier elements. This process, known as the S process, requires two things that a Thorne-Zitkow object would uniquely provide: a source of free neutrons and a relatively cool, high-density environment. The neutron star at the core would provide a torrent of neutrons, and the deep, dense envelope of the red supergiant would provide the perfect incubator for these elements to form. They would then be dredged up to the surface by the star's convection, revealing their spectral signatures to our telescopes. The incredibly high abundance of these elements, especially lithium, which is normally easily destroyed in stellar interiors, is the primary clue that has astronomers so excited. Adding another layer of mystery are the star's own brightness variations. It pulses and changes in light output, which is why it was originally classified as a variable star. However, its specific pattern of variability doesn't cleanly match any known class of variable star. It's not a perfect fit for the rhythmic changes of a Mera variable or the more erratic behavior of a luminous blue variable. This irregular rhythm could be a direct result of its proposed internal structure. The presence of a neutron star core would destabilize the natural pulsations of the red supergiant, creating a unique and chaotic heartbeat that reflects the tremendous struggle happening within, as the gravity and energy of the neutron star interact with the vast, diffuse layers of its host. Of course, such an extraordinary claim requires extraordinary evidence, and the classification of HV 2112 as a Thorne-Zitkow object is still hotly debated. Some scientists have proposed alternative explanations, suggesting it could be a rare type of extremely evolved AGB star or asymptotic giant branch star that has undergone unusual nucleosynthesis. However, the incredible overabundance of those specific heavy elements makes even these alternative explanations push the boundaries of known physics. The unique low-metal environment of the Small Magellanic Cloud may again be the key, providing the perfect conditions for such a strange object to form and for its unusual surface chemistry to become visible to us. If confirmed, the existence of a Thorne-Zitkow object would be a monumental discovery. It would prove that stellar evolution can proceed down a path far more bizarre and circuitous than our simple linear models suggest. It would provide a natural and powerful factory for producing many of the heavy elements in the universe through its unique S process, helping to explain the cosmic abundance of certain elements. Most importantly, it would stand as a testament to the universe's boundless creativity, a place where even the most outlandish theoretical ideas can become reality, waiting in the faint light of a small galaxy for us to finally understand what we are seeing. Stretching across the void between the Small and Large Magellanic Clouds is a celestial river of stars and gas, a structure so vast it defies the very idea of a galaxy as an isolated island. This is the Magellanic Bridge, a tidal filament officially designated SME-1, a gravitational tether connecting the two dwarf galaxies in a slow, cosmic dance that has been unfolding for billions of years. From a distance, it appears as a faint, wispy stream of hydrogen gas, but this is no simple ribbon of inert material. It is a dynamic and evolving structure, a testament to the immense gravitational forces that have shaped and continue to shape the history of our local galactic neighborhood. Its existence tells a story of a close encounter, a violent gravitational embrace that pulled stars and gas from both galaxies, flinging them into the intergalactic medium to form this magnificent arching bridge. The formation of this structure is a classic tale of gravitational interaction, but on a scale that is almost incomprehensible. As the Small and Large Magellanic Clouds orbit each other and our Milky Way, they don't pass by quietly. Their mutual gravity acts like a colossal tidal force. During a particularly close passage, the gravitational pull from the larger galaxy literally stretches the smaller one, drawing out long tendrils of stars and gas in a process known as tidal stripping. Think of it as the cosmic equivalent of the tides on Earth. The Moon's gravity pulls on our oceans, creating a bulge. In this case, the galaxies themselves are the oceans, and the resulting bulge is a stream of material hundreds of thousands of light years long, torn from its home and set adrift between the two galactic bodies. This bridge is the permanent scar of that ancient and violent encounter, a fossil record of the gravitational forces that have governed the motion of these galaxies for eons. What makes the Magellanic Bridge utterly fascinating, however, is not just its origin, but the unexpected life it now contains. Within this vast, diffuse river of mostly hydrogen gas, astronomers have discovered something that should be impossible: pockets of active star formation. This is the central mystery of SME-1. The conventional wisdom of astrophysics states that stars are born in the dense, cold cores of massive molecular clouds, where gravity can overcome internal pressure and cause a collapse. The material in the Magellanic Bridge is thousands of times less dense than a typical stellar nursery in a galaxy. It is incredibly thin and spread out, a near-perfect vacuum by earthly standards, and should be far too tenuous for gravity to ever gather it into a new star. And yet, against all odds, that is precisely what is happening. Scattered along the length of this tidal tail are young, hot, blue stars and small, faint-emission nebulae, the clear signatures of recent stellar birth. This forces a complete rethinking of how stars can form. It suggests that the process of tidal stripping itself is the trigger. As the gas was violently pulled from the galaxies, it wasn't just stretched, it was also compressed. Shock waves rippling through the flowing material could have created localized regions of higher density, seeds of chaos within the stream where gravity could finally get a foothold. Alternatively, the sheer pressure of the gas clouds colliding within the stream as it settled could have provided the necessary compression. These stellar infants are true orphans, born far from the dense galactic cores that are considered their natural homes, thriving in an environment we once thought was utterly barren. Their very existence proves that the universe can find a way to create light even in the most unexpected and hostile of places. The presence of these young stars also acts as a powerful chemical tracer, revealing the bridge's dual ancestry. By analyzing their light, astronomers can determine their composition. Some of these stars show the metal pore signature characteristic of the Small Magellanic Cloud, while others carry the slightly richer chemical fingerprint of the larger galaxy. This confirms that the bridge is not made from materials stripped from just one victim. It is a tangled mixture drawn from both galaxies during their encounter. It is a celestial melting pot, a blend of two different galactic environments now coexisting in a single structure. This intermixing could itself be a catalyst for star formation, as chemically distinct gas clouds collide and create new regions of instability. Studying the Magellanic Bridge in detail provides a unique opportunity to witness galactic evolution in action. We are essentially watching the gradual dismantling of two small galaxies by their interactions with each other and with the immense gravity of the Milky Way. This process is a miniature version of the hierarchical galaxy formation that has built large spirals like our own over billions of years. The bridge shows us how galaxies can exchange material, how they can be pulled apart, and how new stellar populations can emerge from the debris of these cosmic collisions. It is a living laboratory for testing our theories of gravity, star formation, and galactic dynamics, all playing out right on our cosmic doorstep. This vast tidal structure is far more than a pretty arc in the sky. It is a dynamic and violent chapter in the ongoing story of the Magellanic Clouds, a chapter that is still being written. But even the cosmic river of the Magellanic Bridge, with its orphaned stars, cannot prepare us for the sheer strangeness of our next discovery, a signal from the void so precise and unwavering that it feels almost artificial. This is PMN J0048-7307, a radio source that stands as one of the most perplexing enigmas in the entire Small Magellanic Cloud. It broadcasts with a powerful and steady voice in the radio part of the spectrum, yet when astronomers turn every other kind of telescope toward its coordinates, they are met with a profound and unsettling silence. There is no visible star, no glowing cloud of gas, no X-ray signature, and no infrared heat glow. It is a disembodied voice in the cosmic dark, a signal with no apparent source, defying all attempts to classify it with known celestial phenomena. The most immediately baffling characteristic of this object is the astonishing stability of its radio emissions. In the natural universe, particularly in the chaotic environment of a star-forming galaxy, variability is the rule. Pulsars spin down, stellar flares erupt, and accretion disks flicker. PMN J0048-7307 does none of this. Its radio output is rock solid, a perfectly steady beacon that shows no fluctuation in intensity over time. This kind of metronomic consistency is incredibly rare in nature. It suggests an emission process that is not subject to the turbulent, chaotic physics that govern most astrophysical plasmas. Instead, it points to a highly ordered and stable engine, something that can maintain a constant output for years on end without wavering. This unwavering signal is the first major clue that we are dealing with an object that operates by a fundamentally different set of rules. This mystery is compounded exponentially by its location. Precise astrometry has pinned this radio source squarely in the middle of a region brimming with the violent activity of recent star formation. This is a neighborhood of massive, short-lived stars, energetic stellar winds, and the expanding shells of supernova remnants, an environment defined by immense energy and constant turbulent change. It is the last place one would expect to find such a serene and unchanging radio beacon. Any natural object powerful enough to produce such a strong radio signal in this region should also be producing a host of other emissions across the spectrum: X-rays from shocked gas, infrared light from warm dust, and visible light from ionized plasma. The fact that we see absolutely nothing else suggests that this object is either somehow immune to the physics of its surroundings, or that it is not a product of that environment at all, but rather an unrelated interloper whose projected position is a mere coincidence, a possibility that astronomers find statistically very unlikely. The most disconcerting aspect of PMN J0048-7307 is how its unnatural regularity echoes technology far more than it does nature. Its signal profile bears a striking and uncomfortable resemblance to man-made radio sources like those from communication satellites or deep space probes. These engineered transmitters are designed for stability and clarity, to carry information across vast distances without degradation. Natural cosmic radio sources, by contrast, are almost always messy, driven by plasma instabilities, gravitational shocks, or chaotic magnetic reconnection events. They crackle, pop, and fade. This source does none of that. Its pure, stable tone is exactly what we would expect to hear if we were to point our radio telescopes at a piece of technology, a fact that has inevitably led to more speculative discussions about its origin. However, its immense power and location in another galaxy effectively rule out any terrestrial or human-made explanation. This is a signal coming from 200,000 light-years away, and its power requirement is on a stellar scale. Astronomers are therefore left with a short list of exotic natural explanations, each with its own profound implications. One possibility is that we are seeing a rare type of magnetar, a neutron star with an unimaginably powerful magnetic field that is in a uniquely stable state. Perhaps its magnetic field is configured in such a perfect, rigid structure that its radio emissions are channeled with a consistency we've never before observed. Another theory points toward a binary system containing a black hole that is accreting material at an incredibly steady and smooth rate from its companion, creating a stable jet that we see pole on. A more exotic idea involves a so-called diodosphere, a theoretical region around an electrically charged black hole that could potentially produce coherent radio emission. Each of these ideas pushes the boundaries of known physics, requiring conditions or object states that are purely hypothetical. PMN J0048-7307 serves as a humbling reminder that for all our cataloging of pulsars and nebulae, the universe still holds phenomena that we cannot easily categorize. It is an anomaly that refuses to fit into our neat boxes, a signal that challenges us to broaden our understanding of what is possible. It underscores the fact that when we point our telescopes at the sky, we are not just looking for answers to questions we have already asked, we are also listening for the new questions the cosmos is waiting to pose. This mysterious radio source is one of those questions, a steady, silent pulse in the dark urging us to keep listening and to keep wondering. Nestled within the hazy borders of the Small Magellanic Cloud, the star cluster NGC 265 should be a familiar sight, a brilliant, young family of stars burning with the blue-white intensity of stellar youth. At first glance, it fits the profile perfectly, but peer a little closer and this cluster begins to reveal a population of rebels, stars that are behaving in ways that defy the standard playbook of stellar physics. These are the blue outliers, and their existence is sending ripples through our understanding of how stars are born and live in environments different from our own. The most immediate sign that something is unusual in NGC 265 is the sheer, almost excessive, blueness of many of its stars. A star's color is a direct indicator of its surface temperature. The hotter the star, the bluer it appears. In a typical young cluster, you expect a range of colors, from the scorching blue O-type stars to the cooler, redder, lower mass stars. Here, however, there is a surprising overabundance of stars at the extreme blue end of the spectrum. Their surface temperatures are significantly hotter than their mass and age would suggest, making them stand out like brilliant sapphires against the more expected diamond white of their cluster siblings. This isn't just a matter of being young and hot. These stars are operating at a fever pitch that doesn't align with standard evolutionary tracks. This leads to the even more puzzling characteristic of these outliers, their incredible luminosity. They are not just unusually hot, they are also shining with a brightness that is disproportionate to their mass. It's as if a compact car had the engine and output of a Formula One race car. This combination of extreme heat and extreme brightness creates a profound mystery. According to our models, a star of a given mass and age should have a very specific size, temperature, and luminosity. These blue outliers are breaking those fundamental relationships, occupying a region of the temperature-luminosity diagram where no stars should logically exist. They are living a stellar lie, presenting themselves as something they, by all rights, should not be able to be. The most compelling theory to explain this bizarre behavior points to the phenomenon of rapid stellar rotation. It appears that these blue outlier stars are spinning at breakneck speeds, much faster than their counterparts in metal-rich galaxies like our own Milky Way. This furious rotation is not just a minor detail, it fundamentally changes the star's physics from the inside out. A rapidly spinning star becomes oblate, bulging at its equator like a cosmic pumpkin. This change in shape alters how gravity operates across its surface, affecting its internal pressure and temperature gradients. Critically, the rotation also churns the stellar interior, mixing the star's contents like a giant blender. This internal mixing is the key to the mystery. In a normal, slowly rotating star, the hydrogen fuel in the core is consumed, and the byproduct of fusion, helium, accumulates there. Eventually, the core runs low on fuel, and the star begins its evolution away from the main sequence, changing in color and brightness. But in these rapidly rotating mix masters, fresh hydrogen from the outer layers is constantly being dragged down into the core, while helium is hauled away to the surface. This process effectively stokes the furnace, providing a new supply of fuel to the nuclear fires and allowing the star to maintain its high temperature and luminosity for a longer period. It delays the star's aging, effectively allowing it to act like a much younger and more massive star than it truly is. The star is not breaking the laws of physics. It is finding a loophole, using rotation to optimize its fuel consumption in a way we rarely see elsewhere. The reason this phenomenon is so pronounced in NGC 265 and in the Small Magellanic Cloud in general is directly tied to the galaxy's primitive nature. Its low metallicity, its lack of heavy elements, creates a perfect environment for fostering these stellar speed demons. In a metal-poor environment, stellar winds are significantly weaker. A star's wind is like a brake. As material is ejected, it carries away angular momentum, slowing the star's spin. Without these strong winds acting as a braking mechanism, stars can maintain their initial rapid rotation much more easily throughout their lives. Furthermore, the star formation process itself in these low metal clouds may be different, perhaps creating stars that are born spinning faster from the very beginning. The blue outliers of NGC 265 are therefore not just curiosities. They are living relics of a bygone era, showing us how the first generations of stars in the early universe might have behaved massive, blisteringly hot, and spinning so fast they stretched the very definitions of stellar life. Drifting through the intergalactic void on a collision course with the Small Magellanic Cloud is a ghostly, silent intruder known as HVC 306-2+230. This is no ordinary cloud of gas. It is classified as a high-velocity cloud, a massive bundle of primordial hydrogen moving at a speed that defies the gravitational pull of its host galaxy. Its trajectory suggests it did not originate within the Magellanic System, but is instead an external object, a celestial wanderer that has been captured and is now plunging into the galaxy's outer reaches. What makes this particular cloud so captivating to astronomers isn't just its origin story, but the profound and puzzling influence it seems to be having on its new environment, an influence that begins with the highly unusual molecules discovered within its chilly depths. When astronomers analyze the light from background quasars as it filters through the cloud, they are given a detailed chemical fingerprint of its composition. The results are startling. Alongside the expected hydrogen, the cloud contains a detectable abundance of complex molecules, including carbon monoxide and even traces of organic compounds. This is the first major mystery. High-velocity clouds are typically thought to be composed of pristine, unprocessed gas, remnants from the Big Bang that have never been cycled through a star and thus should be devoid of the heavier elements needed to form such molecules. The presence of these compounds suggests that HVC 306-2+230 is not a virgin cloud after all. Its gas has been somehow enriched, polluted by the ashes of a past stellar generation. This points to a dramatic history. Perhaps it was torn from the outer disk of a larger galaxy long ago, or maybe it has swept through and incorporated material from a previously undetected galactic filament, collecting these complex molecules like a cosmic sponge during its eons-long journey through the dark. This chemical complexity is the likely key to the cloud's most baffling behavior, its apparent ability to trigger star formation. As this massive structure plows into the tenuous outer halo of the Small Magellanic Cloud, its leading edge is creating immense shock waves and compressing the local gas. In several specific regions along this collision front, astronomers have identified the telltale glimmer of newly formed massive stars. This is profoundly counterintuitive. By all standard measures, HVC 306-2+230 itself is not dense enough to collapse and form stars under its own gravity. Its internal pressure is far too low. So how can something too diffuse to form its own stars cause star formation elsewhere? The answer is believed to lie in those complex molecules. Carbon monoxide, in particular, is an exceptionally efficient coolant. As the cloud collides with the galactic halo, the shock waves compress and heat the gas. The CO molecules allow this heated gas to radiate away its thermal energy much more effectively than pure hydrogen ever could. This rapid cooling reduces the internal pressure of the gas clumps, allowing gravity to overcome its resistance and initiate the collapse into new stars. The cloud isn't providing the bulk of the mass for these new stars, it is providing the catalyst, the crucial trigger and the cooling mechanism that allows the existing galactic material to condense. It's a case of a celestial visitor providing the match while the galaxy provides the fuel for the fire of creation. The origin of this mysterious cloud remains one of its deepest puzzles. Its trajectory and velocity suggest it is not a native of the Magellanic System. So where did it come from? One compelling theory is that it is a fragment of the Magellanic Stream, a vast, ribbon-like structure of gas that stretches across the sky, torn from the Magellanic Clouds by tidal forces during their close encounters with each other and with the Milky Way. Perhaps this cloud is a denser knot within that stream, now falling back onto its parent galaxy in a cosmic example of recycling on an epic scale. Another, more exciting possibility is that it is a true intergalactic interloper, a remnant from the formation of the local group of galaxies that has been wandering in solitude for billions of years before being gravitationally captured. Its unusual chemistry would then be a fossil record of its ancient and isolated past, a sample of the material that exists in the vast voids between galaxies. Determining its true origin is more than just an academic exercise. It would provide crucial insight into how galaxies accrete fresh material from their surroundings to fuel future generations of stars, and it would give us a rare look at the composition of the truly intergalactic medium, an environment that is still largely unknown and unexplored. HVC 306-2+230 is a dynamic and transformative phenomenon, a relatively small structure that is punching far above its weight, demonstrating how even the most diffuse objects can become powerful agents of change in the ever-evolving story of a galaxy. Moving from the strange regularity of that mysterious radio source, we descend deeper into the high-energy spectrum, to a patch of darkness that doesn't just hide its secrets, but actively toys with those who seek to find them. This is the X-ray ghost, officially catalogued as CXOUJ005047.9-731817. It is not a steady beacon or a predictable pulsar. It is a cosmic will-o'-the-wisp, a source of powerful X-rays that flickers into existence for brief, tantalizing periods before vanishing back into the void without a trace. Its appearances are so fleeting and unpredictable that pinning it down has become a maddening endeavor for astronomers, a game of hide and seek played across 200,000 light-years. The most immediately baffling aspect of this ghost is its pattern of variability, which defies all known categories. Most transient X-ray sources follow some form of logic. They might flare up on a predictable schedule tied to an orbital period, or they might erupt and then fade away over a timescale of weeks or months in a way we can understand. The X-ray ghost does neither. It can remain completely invisible for years with not a single X-ray photon detected from its location. Then, without any warning, it will suddenly switch on, becoming a moderately bright source for a period of days or weeks, only to abruptly disappear again just as quickly. There is no rhythm, no pattern, and no discernible trigger for these apparitions. It's as if a cosmic hand is flicking a switch at random, allowing us brief glimpses of a powerful engine before shutting it off again, leaving us with nothing but questions. This on-off behavior is not just unusual, it is unprecedented in its sheer unpredictability. When astronomers have managed to catch the source during one of its active phases, the data they have collected only deepens the mystery. The X-ray spectrum of the ghost, the detailed breakdown of its energy output, is a bizarre hybrid that doesn't match any known type of celestial object. It doesn't cleanly align with the spectrum of a typical X-ray binary, where a neutron star or stellar mass black hole is accreting material from a companion. It also doesn't match the expected signature of an ultra-luminous X-ray source, or ULX, often thought to be potential intermediate mass black holes. Instead, it shows features of both, blended together in a way that suggests we are seeing accretion physics operating under a set of rules we have not yet defined. The spectrum indicates the presence of a very hot, compact corona of plasma, but its properties seem to change dramatically even during its short periods of activity, as if the accretion disk itself is fundamentally unstable. This bizarre behavior has made the X-ray ghost a prime candidate for one of astronomy's most sought-after prizes, an intermediate mass black hole. These are the missing link between stellar mass black holes and the supermassive monsters that anchor galaxies. Theory suggests they should exist, with masses ranging from a few hundred to a few 100,000 times that of our Sun, but conclusive evidence has been incredibly hard to find. The erratic flickering of this source could be explained by the feeding habits of such an object. An intermediate mass black hole would possess a gravitational sphere of influence larger than a stellar mass black hole but smaller than a supermassive one. It could be orbiting through a region of space that contains only sparse, clumpy clouds of gas, rather than a steady companion star. In this scenario, the black hole would only light up in X-rays on the rare occasions when it intercepts one of these dense gas clouds, devouring it in a brief, violent outburst before returning to quiescence as it moves through emptier space. The strange spectral features could then be the result of this sporadic and messy accretion process, unlike the clean, steady stream from a binary system. However, the ghost refuses to be easily categorized. Alternative explanations are just as compelling. It could be a stellar mass black hole in a highly unusual binary system with a companion star that has a tremendously eccentric orbit or a highly unstable stellar wind, causing erratic and huge fluctuations in the amount of fuel delivered. Or it could be something even more exotic, like a magnetar, a neutron star with an unimaginably powerful magnetic field that is experiencing rare and catastrophic crustal fractures, releasing bursts of energy that we see as these temporary X-ray apparitions. Each time it vanishes, the mystery grows as astronomers are left to wonder if they will ever capture enough data during its next brief appearance to finally solve the puzzle. The X-ray ghost is a reminder that for every rule we write about the cosmos, there are exceptions lurking in the data, faint whispers from the dark that challenge us to keep looking and to keep questioning everything we think we know. Lurking within the faint glow of the Small Magellanic Cloud is a cosmic onion, a planetary nebula whose layers of glowing gas tell a story of a star's death that was anything but simple. This is LIN 41, and at first glance it appears as a fairly typical, if somewhat faint, end-stage star. But when astronomers peel back its layers with powerful telescopes and spectrographs, they uncover a nest of concentric shells and a central engine that defies every expectation, making it one of the most chemically and structurally peculiar objects of its kind ever discovered. The most immediately striking feature of LIN 41 is its intricate shell structure. Most planetary nebulae show a single, often bipolar, shell of ejected material, the final gasp of a dying star. LIN 41, however, boasts multiple distinct concentric shells, like the rings of a tree trunk that record years of growth. Each of these delicate rings represents a separate, violent episode of mass loss from the central star, occurring at different times in its final death throes. This isn't the story of a single, catastrophic eruption, but of a series of dramatic heaves, as if the star was convulsing over thousands of years, periodically expelling its outer layers before settling down again. The precise mechanisms that could cause such repeated and energetic outbursts are still poorly understood, suggesting a far more unstable and erratic end-of-life process for some stars than our current models allow. At the heart of this layered wonder sits the engine responsible for it all, the central star. This white dwarf is the exposed, ultra-hot core of the original star, and it is behaving in a way that is utterly baffling. Astronomers have observed that its surface temperature fluctuates significantly over relatively short timescales. Such variability is not unheard of in white dwarfs, but in LIN 41, it occurs with a bizarre and illogical twist. These large changes in temperature happen without any corresponding change in the star's overall brightness. In stellar physics, temperature and luminosity are deeply connected. If a star gets hotter, it should also get brighter. The fact that this one does not suggests that something is fundamentally wrong with our understanding of the star's structure. One compelling theory posits that we are not seeing changes in the star's internal energy output, but rather shifts in the opacity of its own atmosphere. Perhaps violent pulsations are temporarily inflating the star's outer layers, making its surface cooler and larger, with the two effects cancelling each other out to maintain a constant luminosity. Alternatively, a nearby, unseen companion star might be influencing its behavior, though no such partner has yet been detected. The greatest mystery of LIN 41, however, is written in the light emitted by its glowing shells. When astronomers analyze this light through spectroscopy, they are given a detailed inventory of the nebula's chemical composition. The results are nothing short of shocking. The gas is incredibly enriched with certain products of nuclear fusion, particularly nitrogen and helium. This specific pattern of enrichment is the unmistakable signature of hydrogen burning via the C&O cycle, a process that occurs in the cores of much more massive stars. The problem is that the estimated mass of the central white dwarf remnant suggests its progenitor was a star of low to intermediate mass, a type of star whose core should not have been hot or dense enough to support such efficient C&O cycle burning and to then dredge those products up to the surface. It's as if a compact economy car's engine was found to have the high-performance internal components of a racing Ferrari, a combination that simply shouldn't be possible. This chemical paradox forces astronomers to consider radical alternatives. Perhaps our understanding of mass loss in these stars is incomplete. Maybe the progenitor star was actually more massive to begin with, but shed an extraordinary amount of its mass through a previously unknown hyperwind phase before we ever started observing its final act, fooling us into thinking it was always a lighter star. Another fascinating possibility involves the influence of a binary companion. If the central star was once part of a close binary system, mass transfer between the two stars could have stripped away its outer layers prematurely, revealing the chemically processed inner layers that would normally remain hidden deep within a star of that mass. This would mean we are not looking at the death of a typical star, but at the exposed core of a star that had its evolution violently accelerated by a cosmic partner. Each concentric shell of LIN 41 is therefore a page in a complex and unfinished biography, a story of nuclear processes, violent instability, and a stellar death that challenges the very definitions we use to categorize the end of life in the cosmos. And now we arrive at a cosmic engine of such raw power that it pushes the very limits of what physics allows, a beacon of high-energy radiation that stands apart even in a galaxy brimming with stellar wonders. This is the ultra-luminous X-ray source known as NGC 346X1, a name that belies its truly extraordinary nature. Nestled within the vast, bustling star-forming region NGC 346, this object isn't merely bright in X-rays. It is stupendously, almost impossibly luminous, shining with the power of 1,000,000 suns, all concentrated into a single, searing point of high-energy light. Its output is so immense that it flirts with a fundamental cosmic speed limit, a boundary set by the laws of physics themselves, making it one of the most compelling and enigmatic objects in the entire Small Magellanic Cloud. The sheer scale of its energy output is the first and most staggering clue to its bizarre nature. To achieve such incredible luminosity, an object must be accreting or consuming material at a ferocious rate. The most widely accepted model for such a process involves a black hole pulling gas from a companion star, heating it to millions of degrees as it spirals inward and releasing that energy as X-rays. But there's a catch, a universal law known as the Eddington limit. This is a theoretical ceiling for luminosity, a point where the outward pressure of all the radiation being generated finally equals the inward pull of gravity. At this limit, the radiation pressure is so powerful that it should literally blow away the incoming stream of material, shutting off the accretion process and capping the brightness. NGC 346X1 doesn't just approach this limit. It consistently operates at or near it, blasting out X-rays with an intensity that should, by all rights, be self-extinguishing. It is a cosmic engine running at maximum revs without ever seizing up, defying our expectations of how such systems regulate themselves. This impossible brilliance immediately raises the question of what kind of gravitational monster could possibly be at the heart of this system. A typical stellar mass black hole, formed from the collapse of a single massive star, simply does not have the gravitational grip to hold onto an accretion disk that is producing so much radiation pressure. The leading, thrilling explanation is that we are looking at something much rarer, a potential intermediate mass black hole. These are the elusive missing links in the black hole family, with masses ranging from hundreds to hundreds of thousands of times that of our Sun, bridging the gap between stellar mass black holes and the supermassive giants that anchor galaxies. An object of this size would have a much deeper gravitational well, allowing it to maintain control over its accretion disk even under the extreme radiation pressure that would obliterate a smaller system. The incredible luminosity of NGC 346X1 is one of the strongest indirect pieces of evidence that such an object might be lurking within this star cluster, a gravitational titan feeding at a frantic pace. Yet, when astronomers search for the source of all this fuel, they are met with a profound contradiction. Every black hole needs a donor, a companion star whose material it can steal. In most ultra-luminous X-ray sources, this companion is a massive, bloated star, its outer layers loosely bound and easily stripped away by the black hole's gravity. But the counterpart star associated with NGC 346X1 appears to be all wrong. Observations suggest it is a relatively small, hot star, one that should have a very strong gravitational hold on its own material. Its stellar wind should be weak, providing a meager trickle of fuel, not the colossal downpour required to power such a brilliant X-ray fountain. It's like trying to supply a massive hydroelectric dam with water from a garden hose. The source is utterly insufficient for the observed output. This mismatch between the apparent donor star and the phenomenal energy production is a central puzzle, suggesting either that our observations of the companion are misleading or that we are fundamentally misunderstanding the accretion process in this extreme environment. The unique conditions of the Small Magellanic Cloud may hold the key to resolving these contradictions. The galaxy's low metallicity, its lack of elements heavier than hydrogen and helium, creates a perfect storm for such an unusual object to exist. In a metal-poor environment, stars have weaker stellar winds. This allows the donor star to hold onto its mass much more effectively throughout its life, potentially becoming more massive than a similar star in a richer galaxy. Furthermore, the accretion disk itself would be different. With fewer heavy elements, the disk material is more transparent. This transparency is crucial. It allows the intense radiation to escape more easily instead of being absorbed and re-radiated within the disk, which would build up even more pressure. This altered physics might allow the system to somehow circumvent or supersede the standard Eddington limit, permitting a much higher flow of material onto the black hole without it being blown away. In this primitive galactic environment, the normal rules of accretion may not apply, allowing NGC 346X1 to operate in a regime of extreme power that we have yet to fully comprehend. It is a masterpiece of cosmic engineering, built according to a set of blueprints we are only just beginning to decipher. From ghostly supernova remnants to stellar vampires and phantom radio sources, the sheer diversity of strange objects we've explored within the Small Magellanic Cloud paints a picture of a universe far more creative and chaotic than we ever imagined. Each of these 30 cosmic oddities is more than just a curiosity. It is a direct challenge to our understanding of astrophysics. The perfect ring of a supernova remnant questions the violence of stellar deaths. The missing intermediate mass black holes force us to reconsider how gravity builds structures. The runaway pulsar with conflicting ages demands we rewrite the life story of neutron stars. Every single one of these mysteries exposes a gap in our knowledge, a place where the universe operates by rules we have yet to fully decipher. What makes this small, seemingly humble galaxy such a prolific factory for the bizarre is its unique primordial nature. Unlike our metal-rich Milky Way, the Small Magellanic Cloud is a living relic of the early universe, a place where the lack of heavy elements changes the fundamental rules of stellar life and death. Here, stars can spin faster, burn hotter, and hold onto their mass longer, leading to evolutionary paths that are simply impossible elsewhere. Its low-density environment allows structures like the Magellanic Bridge to form, creating stellar nurseries in the void, while its turbulent history of galactic collisions provides the raw material for endless cosmic drama. This dwarf galaxy is not a simpler version of our own. It is a completely different kind of laboratory, one that showcases the incredible variety of ways the cosmos can assemble itself. The enduring lesson from our journey is that the universe is overflowing with phenomena that defy our neat classifications. Objects like the Thorn-Zitkow candidate or the infrared ghost remind us that for every answer we find, a dozen new questions emerge. The true value of these discoveries isn't just in cataloging strange sights. It's in the way they force us to innovate, to question our foundational models, and to develop new tools and theories to make sense of it all. The Small Magellanic Cloud, our tiny galactic neighbor, has proven itself to be one of the most powerful engines of scientific discovery, pushing the boundaries of what we thought was possible. As we look up at the night sky, it's worth remembering that these mysteries aren't confined to distant, unreachable realms. They are right here in our own cosmic backyard, a mere 200,000 light-years away. If such a small patch of sky can hold so many secrets, it begs the question, what other cosmic oddities are waiting to be discovered, not just in the depths of space, but in the seemingly familiar corners of our own local group? The hunt is far from over. New telescopes and technologies will undoubtedly reveal even stranger objects, each one a new piece in the infinite puzzle of our universe. We want to hear from you. Which of these 30 strange objects did you find the most fascinating? Was it the violent tantrums of R40, the perfect symmetry of SMP-28, or the profound darkness of the missing black holes? Share your thoughts in the comments below, and let's keep wondering about the incredible strangeness waiting for